First say hello everyone, welcome for today's quantum spacetime seminar. Today we are very happy to have Pratik Rath from Santa Barbara, and he's going to tell us about page curve for reflected entropy. Over to you, Pratik.
Thank you so much. Firstly, thank you so much for the invitation. It's really a pleasure to be giving a talk at TIFR, a place that's in my hometown, Mumbai. And as I was telling people earlier, like it played a big part in my choice of choosing to pursue physics. So I'm really honored to have this invitation. What I'd like to tell you about today is the page curve for reflected entropy. Hopefully these things become clear as I proceed with the talk. But a cartoon of what I'll talk about is this plot. So hopefully you should be able to understand each thing in this plot by the end of the talk. This is some work in progress with my collaborators, Chris Akers, Tom Faulkner, and Simon Lin. It's been a work in progress for a while, but hopefully it should be out maybe sometime this month. So let me start with some broad motivation first. The general program in which I'm quite interested in is colloquially called the it from qubit program, or in other sometimes also called ER equals EPR and so on, where the key idea is that somehow entanglement in quantum systems plays a key role in the emergence of classical geometry, the description of space-time, especially in the context of holography, which we best understand in and the best understanding of this essentially came from the Ryu-Takenagi formula way back in the day, where people saw that there was a connection between the entropy on the boundary and the area in the bulk. So just to lay down conventions, we have a boundary interval, capital A. The Ryu-Takenagi surface is the minimal extremal surface anchored to its boundaries, which I'll call gamma A. And this region A is a Cauchy slice, a partial Cauchy slice that bounds the region in between the Ryu-Takenagi surface and the subregion, which I'll call the entanglement wedge. So it's been a while since we've learned about the Ryu-Takenagi formula. There have been proofs about it. There have been various generalizations. And it all culminated in our understanding of the encoding of the bulk on the boundary in terms of quantum error correction. So the success of this program has been to understand the mechanism by which bulk observables, which have a low energy classical, semi-classical description, are encoded on the boundary. And in particular, subregion duality is the statement that the information that's in the bulk in this region is completely captured by this boundary subregion. So this is something that we've understood for a while now. What would I like to do? Well, we'd like to go beyond this in a few ways. So firstly, the Ryu-Takenagi formula is sort of a coarse understanding because...
Sorry, could I interrupt you, Pratik? Just to understand, is quantum error correction the same as the statement that there are many different boundary operators that yield the same bulk operator?
I think you could say that. When I say quantum error correction, I wanted to say sort of the contrapositive of that. Like what I wanted to say was a single bulk operator, for example, here, would be reconstructed on A as well as on another subregion. Maybe that's the same as what you said.
Right. Okay, and that statement you call quantum error correction. I mean, you know, by quantum error correction, you don't refer to these detailed tree kind of things that people draw in the bulk. So the detailed models of the error correction, just the statement.
So I will get to those as well, and I think they will also play a key role. But as of now, what I mean is just the feature that there is a redundant encoding of a particular bulk operator on the boundary.
Thank you.
Thank you for the question. Also, please do ask questions. It would be helpful just for me to gauge where I'm pitching the. Okay, so as I was saying, the Ryu-Takenagi formula is a rather coarse description because the entanglement entropy is good at measuring bipartite entanglement, but not so much when you have multiple parties. So as we want to refine the structure, like in this previous picture, we just drew these two intervals. And we wanted to understand the entanglement structure between them. The entanglement entropy is good enough to do that. But in general, we'd like to have a finer understanding of how the bulk is encoded on the boundary and how entanglement plays a big role in this. And in order to do so, we'd have to have finer entanglement measures, which are good at measuring multipartite entanglement. In the quantum information community, people have a lot of these measures, which can capture, say, tripartite entanglement and higher party entanglement. And we'd like to find something similar like that and understand how geography requires it or uses it, or how geometry arises from that sort of entanglement. So that will be one theme of this talk. The other theme is sort of related to what Shiraz was asking about, which is tensor networks. So tensor networks are a more detailed version of quantum error correction, which for a while have now been understood as decent toy models of holography. And people learned that it has something like a Ryutakianagi formula, it has this quantum error correction encoding and so on. But what I'd like to emphasize is that these toy models are actually unreasonably effective. They actually capture a lot of the non-perturbative features of the gravity path integral, which are rather surprising. So one of the things would be to emphasize how tensor networks are useful in understanding this entanglement structure in holography. And the other theme of this talk would be to sort of reverse the arrow, and instead of going from geometry to entanglement, a lot of the things are like we have a geometry and we use it to compute entanglement measures. We'd like to go reverse and start with something like an entanglement structure and build up geometry in some suitable environment. So these would be the broad themes of this talk. Okay, so with that, let me give you an overview of what I'll talk about. So first, let me explain the terms that show up in the title. So firstly, I'll talk about the reflected entropy, which is the key player in this talk. Then I'll talk about what page curve we're describing here. And I'll do so in a particular toy model in some detail, which is a model of JT gravity coupled with end of the world brains. It's a toy model that's familiarly called the West Coast model. And we'll be able to understand this page curve in a lot of detail in this particular toy model. Using that as inspiration, I'll talk about some more models where we can understand this page curve rather well, which are tensor networks. And in some particular sense, the calculation I do in the context of JT gravity will actually almost be a part of the tensor network calculation, and the tensor network calculation sort of generalizes it. Using tensor networks, I'll then describe how we can think about geometry as coming from some building blocks and how we can build more and more complex geometries from that basic structure. And finally, I'll summarize and talk about some future directions that we're thinking about. Okay, so let's get started. The reflected entropy is defined by using something that's called the canonical purification. So the canonical purification is defined as follows. We start with some density matrix defined on a two-party system on A and B. This density matrix is an operator acting on the Hilbert spaces of A tensor B. And we can canonically purify it by considering the square root, which is essentially, we take the square root of this operator and think of it as a state. So this state now lives on a doubled copy of the Hilbert spaces of A and B. So there's HA, tensor HA star. A star is something I'll refer to as the reflected copy of A. So it's just some double copy of it. And similarly, HB, tensor HB star. B star is the reflected copy of B. This might not be as familiar, but there's a particular example where we do this all the time, which is the thermofield double. The thermal state is a density matrix on some Hilbert space, and a particular purification of it that we like is the thermofield double, which purifies it into a doubled Hilbert space. So the canonical purification in general is just the same procedure, but applied to arbitrary subsystems. Given this, the reflected entropy is defined as follows. The reflected entropy between A and B is just the entropy of AA star, so A and its reflected copy, in the particular state, which is the canonically purified state. Okay, So this was something that was proposed in a paper by Shouvik Datta and Tom Faulkner. And we'll see why it's interesting in holography.
Pratik, really sorry, I was having internet issues. Could you say in just 10 seconds again what your definition of canonical purification is, please?
Yes. So the canonical purification is, so we take, so there's some operator rho AB, which is the density matrix. We just think of its square root. And there's a Hilbert space. There's a canonical Hilbert space, which can be defined on a doubled copy of the original Hilbert space, which is essentially, we think of the Hilbert space of operators. And this is a state living on that Hilbert space. In particular, it has the nice feature that when you reduce to the original A and B, you end up with the density matrix rho AB. And it's something that's very analogous to when we go from the thermal state to the thermofield double.
Thank you so much.
Pratik, may I ask?
Yes.
Yeah, so the in this example, I understand this example of, I know this example, of course, but what are A and B in the example?
Yeah, good. So here, all I used was that AB was the full system on one side, which is what we normally think about. You can think of it as like half space of, say we have a two-sided black hole, and like we're taking the density matrix of the right side and splitting it into two halves. So A and B are like half spaces of the right side.
I would call it only A, and the left copy would be A star.
You could do that. I mean, that would be the particular case where B is empty. Here, I mean, everything like A and B go together here. So you could call it what you like. But once we measure something like S of A star, then it'll be important what the specific bipartition is. What I mean is you could choose anything, like if this is one boundary, you could pick even like B to be something like this and A to be the union of these two.
Ah, okay, got it. I see.
It doesn't matter for the canonical purification.
I got it. Okay, thank you.
Thank you for that question. Any other questions?
And I guess the important point is that the entropy somehow of A star will in general be different from the entropy for A itself, yes, etc. And that will encode some of your entanglement.
Yes.
Okay.
How it has a nice holographic picture, and maybe that will clarify it more.
Sorry, I have a question. So this is for bipartite case. Is there an analog? Let's say there are thermophile triple, thermophile. Is there any analog of those kind of thing also?
What do you mean by the thermophile triple?
Like you have three copies, let's say, for example.
Okay.
So is there an analogous definition which does like purification or?
Not that I'm familiar with, because this is a canonical thing that's well defined. I mean, all we're doing is taking the operator and thinking of it as a state, and naturally, like an operator has two indices, so it'll end up with a doubled copy of the Hilbert space. There might be some generalization for like higher tensors or something, where like instead of operators, if you had like 3 index tensors or something, then you could do something like that. But I'm not familiar with anything that does this for the density matrix, or at least in a canonical way. Okay.
And Pratik, how good is the reflected entropy as a measure of multi-party entanglement? But perhaps you're going to explain this later. But
I'll just get to that on the next slide. So
sure.
Good. So let's see why this is such a useful measure holographically. The proposal by Datta and Faulkner was essentially that this takes a very simple form. It has a nice holographic dual, and the holographic dual is the following. So we consider the entanglement wedge of A and B. So for example, let's take 2 intervals in ADS, which are in the connected phase. So we take these intervals to be large enough so that the entanglement wedge is this blue region. And now we define the minimal entanglement wedge cross section, which is the minimal surface that splits this entanglement wedge into 2 parts, one which is homologous to A and one which is homologous to B. The minimal such surface has an area which is defined by EW. And the proposal is that the entropy is given by twice EW divided by the familiar factor of 4g Newton. I'll give you some intuition for why that's true. But before that, let me just answer Onkar's question, which was the reflected entropy has not been studied a lot in the quantum information literature. It was basically proposed because of this holographic dual. And so we don't completely understand how good it is as a correlation measure. There's a very specific inequality that needs to be satisfied for it to be a correlation measure. But if you assume this holographic dual, you can show all of the relevant correlation inequalities using the holographic dual. So it's similar to how we prove inequalities using the Ryu-Takanagi formula. And at least holographically, it seems like a nice measure of correlation. It's still an open question whether it is genuinely a correlation measure that should be studied more in the quantum information literature in settings outside holography. But that's outside the scope of this talk.
I see. So there's no proof, you say, that this minimum cross-section is the reflected entropy?
No. So what I'm saying is there's a reasonable path integral argument for the fact that this minimal cross-section is the reflected entropy. What we don't have a proof for is whether it's technically a correlation measure. So what I mean by that is there's a very specific inequality, which is the following. In order for a correlation measure to really be a correlation measure in quantum information language, you want that the correlation always decreases under the reduction of a system. So the correlations between A and BC should strictly be greater than the correlations between A and B. However, this is hard to prove, just from the definition of the reflected entropy.
I mean, this is a statement independent of holography. Just you have your definition, you're not quite able to prove this. Is that right?
Yes. That's right.
Yeah, but you say there's no proof, but no counterexample.
That's exactly right. So more so, there's no counterexample, and like every numerical study that I know of, which is like, there's no published work, but like from personal interactions, there's no counterexample that's been found. Further, if you assume that, so you could, instead of SR, you could define EW directly, and it's true that EW of ABC is always greater than EW of AB. So this is a true inequality. This can be shown directly from geometry. So if you assume the holographic dual, then it is a correlation measure. But more generally outside holography, it's not clear.
I see. But just, are you going to give us a little bit of the flavor of the proof on the gravity side as to why the reflected entropy is this cross-section?
Yes, so that's my next slide. Let me go to that.
Sorry, Pratik, I just also wanted to ask you whether there is some sense in which the reflected entropy also measures like how separable the density matrix can be.
There is
or not.
There is some statement about it. I mean, so there's some statement of the form, if SR of A and B is 0, then you can write the state in some specific form, which I think is basically separable. Yeah. There's a paper about this. Yes.
I see. Okay. Thank you.
Separable means there could still be entropy. I mean, you mean the original state AB together, rho AB could have been mixed, yes. But it's actually a density matrix rho A tensor product rho B. Is that what you mean?
So general. Yeah, sorry, go ahead.
No, I just meant by separable, you mean like a classical superposition of product states. So there's no quantum entanglement between the two sides, but just classical correlations.
It's something like, I mean, I want to say it's something like this. So you can have, just an unentangled state would have just been this rho tensor, rho A tensor rho B. And you could have a classical mixture of them, and that's still separable. There's basically no entanglement. It's just a classical correlation.
Okay. It's not a tensor necessarily just a tensor product, but a sum of.
Yes, that's right.
It's some product. Okay, got it. Mm-hmm.
Okay, good. So let me give you some intuition for the holographic proposal. So the idea is what we'd like to do is compute the entropy in a particular state, which is this square root rho AB. So one simple way to do this is to find the geometry dual to this square root of rho AB. And what we already know from the previous discussion about subregion duality is that the region of the bulk that rho AB accesses is the entanglement wedge of AB. So what you could do is take one copy of the entanglement wedge and double it into a geometry which looks like the following. So we're taking the picture from before, taking two copies of this blue region and sort of gluing them along these surfaces. This ends up forming a cylinder where one side has A and A prime and the other side has B and B prime. This is sort of the time symmetric slice on which this initial data is prepared. Now, this is nice in the sense, once you reduce to A and B, then clearly just because we doubled the geometry, the entanglement wedge for A and B is the same. So it's strictly a purification. Further, it has this nice symmetry of exchanging AB and A star, B star. And additionally, it's good initial data because it solves the constraint equations. This is something that was shown in a paper by Engelhardt and Wall. The fact that the surfaces on which you're gluing these patches together are extremal plays a key role in the fact that this initial data solves the equations of motion, solves the constraint equations. And so we think of this as, yes.
Sorry, Pratik. The fact that A and A prime sort of join up has to do with the fact that you're taking the same state on A and A prime, or some complex conjugate of the state on A and on A prime. I mean, why are they connected?
Yeah, so I was just saying, like in this picture, if we take two copies of this blue wedge and just glue them together along this region, it would naturally lead to a geometry where A and A prime are connected on one side.
Yeah, no, but I was wondering why we're allowed to glue at the boundaries. That's a physical statement, right? That the state and is that connected to the fact that you have the same state on A and A as an A prime? Is that basically the gluing condition?
That's right. So it's basically the same state on. I think strictly what we're using is it's the same state on AB and A prime B prime, so that we're gluing together these two copies. There's a symmetry in exchanging AB with A prime B prime.
Well, but you're gluing A prime. I'm looking only at the boundaries. You're gluing A prime with A. So that's telling you that the state is sort of going continuously across the boundary of A and A prime.
Oh, you mean why didn't I have B prime here or something?
No. Why wasn't it 4 different intervals? Why was the boundary interval of A connected with the boundary interval of A?
Well, you at least want the entanglement wedges to be identical. So if you had a geometry where A and A prime were split by some amount or something, I can't imagine a situation where you'd have the entire entanglement wedge.
I'm not understanding. I mean, it should follow from your definition, right? If you had chosen a different state on your doubled copy,
yes,
from A prime, some completely different state, I think you would have had 4 different intervals on the boundary. If they were just totally unrelated things. Mustn't it somehow be that A and A prime are the same states, that leads to the continuity on the boundary, or not? Am I being?
I think he's saying that, no, Shiraz, but sorry to interrupt, but because if you took a different state, wouldn't you get a different entanglement wedge in the sense that the back reaction in the geometry would change things?
I suppose. But just, there's a boundary question here, which makes no reference to entanglement wedges, right? You're setting up a path integral on the boundary, and then you solve an ADS-CFT question to fill it up. Right? So there should just be a simple boundary argument that A and A prime are joined together.
Yeah, I mean, yeah. So you could make this argument as using a path integral as well. Like it'll end up giving you the same geometry.
No, the geometry is another matter. At the moment, I want to know what boundary partition, quantity are you computing? Then we can talk about ADS-CFT and fill it up. Right, your definition was just of a boundary quantity, right?
Yes, so we're computing, say, any observable in this particular state, square root rho AB.
Great. So there is a boundary state. You define some boundary doubling, that is given by some boundary quantity, which then you can later fill up with ADS-CFT, I would have thought.
Yes.
Okay, so the boundary quantity, if I understood right, is sort of the path integral with two circles. And I'm trying to understand that. And then I'll later try to understand why you fill it up with this particular.
So Shiraz, one way, can I ask this? So the gluing looks like you're kind of taking the trace, right? Rather than keeping the indices open.
Oh, sorry, maybe this was confusing. So this is just the spatial slice, not the full path integral or something. Like maybe is that the confusion?
No, but even if it's spatial, the question is why are fields continuous along the intersection of A and A prime?
Yeah, I mean, strictly speaking, I suppose A and A prime could be slightly disjoint intervals, right? They're not supposed to be like parts of one circle. But perhaps the picture is misleading, Pratik. Maybe you had in mind that there is some small gap between A and A prime, which is removed out of the picture.
I think so, because like any such picture wouldn't be consistent with the bulk expectation. The reason I say so is because the HRT surface for AB goes all the way, and we'd like to glue together two copies of these. And so it would have A prime glued to the boundary of A without any gap.
Yeah, Shiraz, let me ask you, and Pratik, this, I mean, it seems quite reasonable to me, but let me ask you, suppose, let's just take A itself. You take some field theory living in some space, time, but let's take a particular instant of time and some region of that space, and you want to glue another field theory configuration to that. Continuity is the first thing you would demand, right? At a given instant of time. Suppose you were just solving the classical field equations. Continuity is the first thing you demand, and then you would allow the system to evolve. For that, you might have to give something about the first derivative as well, right? That we can think about in time, that is. But continuity is the first thing you would normally impose, no? Which is what I think Pratik is doing here. Well, you all can correct me.
But isn't this connected to the fact that he's choosing the same state on A and the doubled copy of A? Otherwise, I mean, in general, if you have two different states, or you're saying anyway it would be continuous, and not clear to me, because
I see. Your point is, why does continuity impose the same state condition? Huh?
That somehow put it, I don't know. Yeah, right. I'm confused, I suppose, but it just seems to me that there's something being put in here.
No, I'm just trying to understand. I see. So you're saying, how does this continuity impose that?
Sorry, I'm a bit confused. I mean, I thought the A is entangled, right? So what do you mean, Shiraz, when you say the state on A and A star? Because the pure state only exists in the tensor product of four things.
I mean, if state you mean the density matrix, then what I was saying was that the density matrix on AB is identical to the density matrix on A prime, B prime. And that's the symmetry I was using. Which in particular also means that the density matrix on A is the same as the density matrix on A.
Yeah, that's right. That's how I was interpreting it. Shiraz's point is, how does that necessarily lead to continuity? Huh?
So let's say this is being constructed in the boundary in some scalar field theory, right? Then I think the continuity that Shiraz would want is like as you take the scalar operator closer and closer to the boundary of, say, the A interval, then it should match up with the value of the scalar field as you get closer and closer to the boundary of the A prime interval, right? And presumably that condition is just enforced by this reflected entropy state, right?
Right, that it's the same state, basically.
Yes.
Shiraz, if rho A is the same as rho A prime, at least the expectation value of the field, right, will line up, no?
Yeah, I think that's right.
Yeah.
I just wanted to say that it seems to me that the fact that you've got the same state on both sides is important for this, right?
Yeah, I think I agree with you. There's a symmetry in A and A prime as well. Maybe that's what you wanted. Like, state is exactly the same, yes.
Yeah, okay, right, because there's a sort of Z2 symmetry in your configuration.
Yeah, exactly, yeah. There's a natural map between operators on A and operators on A prime, and they glue up naturally.
Sorry, I'm still a bit confused. I mean, If let's say I take a special case where B doesn't exist, okay, it is null. So
Yeah.
it's more like a thermofield system. Now in thermofield system, how is it that the state now exists on two things glued to each other? I mean, aren't these supposed to be two different systems on which you have states? I mean, on the tensor product of which you define the state, it's not like you take the left boundary and the right boundary and somehow glue it, right? So I'm a bit confused. So for example, here also in this picture, if I take the B to be null, non-existent, then it should be very much like a thermofield system. But there I don't glue the boundaries on top of each other, right?
I mean, I think it's the thermofield system up to these endpoints. Like, I mean, you'd have something like an RT surface here, but you'd have some endpoints, unlike the usual thermofield double.
But when there are no endpoints in particular, then these two systems, the A and A prime, they are not geometrically glued, or I mean, so why are we gluing it here?
Sorry, you mean when A is the entire boundary or something?
Yeah, let's say.
Oh yeah, then they wouldn't be glued together. But the geometric picture would also not require you to glue it together. This was a particular example. In the two intervals example, because you have these boundaries, you do end up gluing them together. But there will be more examples. Like for example, in wormholes, this won't be the case. Like you'd have like separate asymptotic boundaries.
Is there a path integral way of understanding this just from the boundary point of view? Just like, you show replica tricks and things like that, right? Where you define a state with a path integral and then glue it. It would be nice to see it in a transparent way like that.
It is. I just didn't want to get into that. So that's why I gave you this smaller version of the derivation. There is a more detailed path integral derivation in the paper by Datta and Faulkner. And the idea is essentially, it's something we'll use in this talk as well. It's you basically construct something like rho to the m over 2 for even m. This is something that you can do with a path integral, and then you analytically continue to m goes to 1. This prepares precisely this geometry.
Nice. Okay. And in higher dimensions, then this should be these intersections would be spheres, right? It would be sphere fibered on the interval.
Yes.
Higher sphere fibered on the interval. Yeah.
Okay.
Sorry, may I ask a question?
Yeah.
So this, from the boundary point of view, this reflected entropy, how is it different from, let's say, the square root of the second Renyi entropy?
The square root of the second Renyi entropy. Well, it's different because in the square root of the second Renyi entropy, maybe you mean because like you're computing the square root of the state here? Is that the question? Because
I'm just trying to understand, is there any correspondence from the Renyi, replica construction?
Yeah. So I think the key point here is that we're computing, once we do this canonical purification, we're computing the entropy of A star, which doesn't have any analog in the Renyi entropy calculation. Whereas in this, I mean, if you using a very similar path integral, you can prepare the Renyi entropies as well. But what we'll do with it is something more nuanced. So it'll be different from that calculation.
But from the statement that the state on A and A prime should be same, it looks like the Renyi replica construction.
Why do you say so?
Yeah, maybe I'm confused. Maybe
I'm for example, like if we took something like the thermal state, then the Renyi entropies are basically the entropy at like a different temperature. Whereas this would be just like preparing the thermofield double and computing an entropy in the thermofield double. So don't immediately connection to the Renyi entropy.
Sorry, also one more question. You are gluing the endpoint of A to the endpoint of A prime, but the endpoint of A was already glued to the endpoint of C. So
that's right.
Is there a corner there?
There is. Yeah, it's not so clear what happens at that corner. But I think on the QFT side, like at least in 2 dimensions, you can define this nicely and it makes sense. I think it's not clear in higher dimensions on the boundary how exactly this works. But basically in this geometric construction, we're getting rid of C. Like we're taking A, B, and then just purifying it, and we have A prime, B prime. This is a pure state on its own. So we've gotten rid of this C system.
No, but that seems a bit drastic from the point of view of path integral, right? Because the path integral naturally had this continuity across the boundaries of A to C. And now you're making it, so I don't know, it's not totally clear to me, but maybe, yeah, I should go and look at this paper.
No, I mean, I think in general, you're right. In field will be ultraviolet divergences to really care about, but okay, you put it on a lattice and so on, you do something. I think that's true though, what Abhijit says, right? Because you have some continuous field, you chop it in the middle and you glue another copy, and these are violent things to do, right? I think.
No, and also there is C, right? That's coming from the other side.
That's what I meant. I mean, there's C, you chop C, and you glue. I mean, these are violent things to do, I think. Yeah.
And just one more comment along the same lines, in the original path integral, the one with one copy, as Abhijit said, there was A, B, and C, and A and B and C were all part of the same system.
Yes.
Right? The whole boundary had A, B, and C.
Yes.
Here you have an A, B, C, and an A prime, B prime, C prime. And you might wonder whether this picture here is part of one boundary or two, or...
Yeah, that's why the two boundary kind of thing looks natural from the point of view, thermofield. But there is no C prime also here, right? If I'm not mistaken.
Yeah, we're completely getting rid of C and C prime.
Yeah, but if you had a C, you would also have had a C prime. And then is it part of one big system or two? Or I mean, the whole thing could. I had the same question as Abhijit.
Yeah. Okay. I think what you want to say is like, if we start with the original system, then like there was a C glued to these endpoints. And so there'll be a C prime with that. But I think the geometric description of that would be that it's a completely separate geometry. Like this on its own is one connected geometry.
Yeah, but perhaps along the lines of what Abhijit was saying, I was just wondering, just in field theory, the path integral would seem to involve some C and C prime that would be doing something. Anyway, we'll go. Please go on. We'll come back. Yeah.
I should also emphasize that this will not play a big role in the calculation I'm going to talk about, because UV divergences won't be important there. Further, I should also emphasize that this canonical purification is something that's well defined in algebraic QFT as well. So I think the UV sensitivity is taken care of, but I don't want to get into the details of how. Like,
just last comment about this, like Abhijit, my concern was more than just about UV sensitivity. It seems like it was just a different path integral that you would naturally compute. But please go on. I'll let we come back.
Okay, we can get back to this maybe at the end of the talk. Okay. All right. So with that, let me move on to the overview of this talk. So now you know what reflected entropy is, kind of. So let me tell you what page curve we're talking about. So the page curve is pretty simple. Whenever we have an entanglement phase transition, there's going to be a discontinuous reflected entropy transition. So in the disconnected phase here, we have no need for an entanglement wedge cross section because the two homology slices are anyway split from each other. So EW is 0. On the other hand, in the connected phase, there's a non-trivial entanglement wedge cross section. And from the duality, we know that this is some order 1 over G amount. So it's a large number. Further, this jump is discontinuous because the point at which the phase transition happens depends on the areas of these red surfaces, and it has nothing to do with the blue surface itself. So the point at which this transition happens, there is a non-trivial value of the entanglement wedge cross section as soon as you go into the disconnected phase. So the answer jumps from 0 to a large amount very quickly. And so this is something that needs to be understood. Like the page curve for the entanglement entropy is at least continuous. This one is discontinuous. So we'd like to understand what effects give rise to such a transition.
I'm just sorry, Pratik, you really have to go on, I know, but I understand the point you're making, but why do you call it page curve again? And normally I think of page curve as the information coming out as a black hole evaporates or something. I mean, this... what if it's not important, you can go ahead.
It doesn't necessarily have to do with the calculation page did. It's just like, I just wanted to make an analogy with what we do for the entanglement entropy in the context of the page curve. More so the calculation I'll be talking about is something which is related to black hole information. So in that context, maybe you could call it the page curve for a reflected entropy. Right. Anyway, what I want to emphasize is it's just some phase transition.
Yeah.
Okay, thank you for that. Okay, so good. Let me now move on to the calculation that I'd like to describe, maybe go through it a little more quickly. And I hope I can take some extra time, given that there were so many questions.
Don't go through it a little more quickly.
Yes, Pratik, don't worry about the time.
Thank you. Okay, good. So the toy model that I'm going to talk about is what's called the West Coast model. So in this paper by Pennington, Schenker, Stanford, and Yang, these guys described a very simple tractable model, which could be thought of as a model for black hole information. And in that context, they derived the entanglement entropy page curve. And so I'd like to use the same model to understand the reflected entropy, and it'll also turn out to be quite tractable. So let me start by describing this model first. The model is pretty simple. The action is given by Jakiv-Teitelbaum gravity, which has essentially two fields, the metric and the dilaton, and it's coupled to these end of the world branes, which have some mass mu, which we'll take to be large. Similarly, we also take S0, which is the coefficient of this topological term, to be large. And this model gives you solutions of the following form. So in Euclidean, we have solutions that look like this. There's a boundary which has some given renormalized lengths, beta, and there's a end of the world brane that cuts off the solution. And I've marked the extremal surface on this Euclidean solution with this dot. When we analytically continue it into Lorentzian, it looks like this, where there's a black hole horizon and there's an end of the world brane sitting somewhere in the interior.
And Pratik, I must say, I've never really been able to understand this model, although I've tried to study. Let me ask you this. What are the boundary conditions on the end of the brane? And is the variational principle well defined? Sorry, just once, then.
Yeah, it is. So one way of thinking about this end of the world brane construction is by considering geometries where you have sort of where you just double this and you have some boundary like this, and then just perform a Z2 orbifold. This leads to this end of the world branes model. And the boundary conditions you end up imposing here are essentially that it's the midpoint of this Z2 orbifold. So it's a fixed point. So you have these Neumann boundary conditions there. It sits on a geodesic, and the normal derivative of the dilaton is fixed by the mass of the end of the world brane. This is a good variational principle. You can show that it's a good variational principle.
Okay.
Yep. Okay. So in this model, how do we think of this as black hole information? Or
Sorry, Pratik. Normally, when you have a brane, the discontinuity of the extrinsic curvatures across the two ends of the brane is the tension of the brane.
Yes. So here the tension, the tension here is like the mass of the brane. I mean, it's a 1D thing. So there's a discontinuity in the derivative across this. And we're keeping only one piece of it. So the derivative, in two dimensions, the analog of that condition, I think, is the derivative of the dilaton being fixed by the mass.
I see. So extrinsic curvature somehow becomes dilaton.
Yes. I mean, everything here. So area here will mean dilaton, and extrinsic curvature is like derivative of the dilaton and so on.
Thank you.
And no further condition, I take it, on the metric is needed, right?
So the boundary conditions at the brane are just these Neumann conditions, and the boundary conditions at the asymptotic boundary are the usual Dirichlet boundaries. Yeah.
Okay.
All right. Good. So how do we think of this as giving rise to something like black hole evaporation? Well, we don't. This is basically a static situation. But what we can do is think of a state where we have the system B, which is the black hole system, which is this Jakiv-Teitelbaum gravity plus branes, and we couple it to some radiation system. So we think of it as an entangled state where we have the radiation state ij. So we've artificially split it into two parts here because it will be useful for the reflected entropy. So we've broken the radiation into systems R1 and R2. That won't be important for this initial part. But what we do is couple the state such that we have an entanglement between ij, which are the radiation indices, and psi ij, which is the state of the black hole with the branes being in flavor index ij. So we introduce some flavor indices for the brane, which are entangled with the radiation. This is sort of, in an artificial sense, you can think of this as a post-page system, if you like, or like a partially evaporated black hole, where you have interior modes that are entangled with some exterior modes that have been kept in some separate bath region. So we've extracted some of the Hawking radiation from the exterior, kept it in this radiation system, and then we're looking at this entangled state. Good. So how do we
say, sorry, just I know this is, but just the IJ flavor indices of the brain have no gravitational consequences, but they are useful when you come to the radiation. Okay,
that's right. So we're assuming some huge flavor symmetry there, like it doesn't affect the dynamics and so on. And yeah. So,
okay.
Good. So how do we do calculations in this setting? Well, we can compute overlaps between states of the black hole with different brain indices as follows. The boundary conditions for the path integral are, we have these green and orange dashed lines, which represent brain index lines, and they're coupled together by the asymptotic boundary of the black hole, which has some fixed renormalized length beta. So we define these boundary conditions, they compute this overlap, and doing this on the gravity side just corresponds to filling this in with arbitrary geometries. In JT gravity, we understand how to do the path integral, so we can just fill it in with arbitrary geometries of this specific topology in this context. Here, like you can see that the green indices are basically contracted. So that leads to something that's a Kronecker delta on I1, I2, and similarly on J1, J2. So that's sort of the flavor of how we do these calculations. The weights of these calculations are fixed by the action contribution coming from the geometries. Good. So once we know how to compute these overlaps, we essentially know how to think of density matrices. So if we look at the density matrix on the system, the radiation system, it has coefficients that correspond to the overlaps between black hole states with different brain flavors. This basically follows from just taking this and tracing out the black hole system. And so if we want to compute anything that's a function of this density matrix, we basically use diagrammatics that are similar to this. So in particular, an example is when we want to compute trace rho to the n, let's say n is 4 here, when we have 4 asymptotic boundaries, which are glued together cyclically, and this computes trace of rho to the 4th. And if we try to do this on the gravity side, essentially what we do is sum over different topologies. So for example, I've drawn one topology here where 2 of the boundaries are connected together, and there are 2 of them which are disconnected and on their own. The calculation relies on just a few features. There are these index loops corresponding to the green and orange indices. There are 2 of them. There's one here and there's one here. These lead to factors of the number of flavors. So it goes with a factor of k. And each of these geometries correspond to some path integral calculation in JT gravity. So here we've represented these 2 as Z1 squared, where Z1 is the path integral with 1 boundary, and Z2 is similarly the path integral with 2 boundaries. Let me emphasize that in this calculation, we suppress topologies that have higher genus, because they'll be suppressed by powers of e to the s naught, since there's a topological factor there. So they're suppressed in that genus expansion. Further, we also suppress diagrams of the form where these 2 boundaries are glued together and these 2 boundaries are glued together, because these would cross in the bulk. There'll be non-planar diagrams, and they'll be suppressed by in the index loop counting. So they'll be suppressed in powers of k. Since we take both of these numbers to be large, we ignore all of these. So in the end, what we're left with is a sum over planar topologies. Okay, good. So even after doing so, this...
I'm really sorry to trouble you. Could you go back one slide, please? You gave some sort of... I didn't understand the second diagram on this slide. This is meant to be a path integral representation of psi I1 J1 inner product with psi I2 J2.
Yes.
The size was these mysterious states on the world volume of the brain, right?
Yes.
So how do we have a path integral representation for their overlap?
Well, we can think of preparing this particular state. Just this state. This state was prepared by sort of half of this path integral, right?
How did I prepare the state? Did I give boundary conditions at the top and the bottom?
Well,
you are preparing a particular state, right?
Yeah. So let's say we fix the label here. Like, so if I just draw half of this diagram.
I have always exactly the same question as Shiraz. It's okay. The gravity theory really doesn't care about the I index in it, honest to goodness sense. I mean,
yeah, I mean, so okay. Are you asking about what I'm mentioning on this blue line that specifies I or J?
No, I'm just asking you if you could go one slide further. You've given a path integral representation of the state.
Yes.
And I wanted to understand where you got that from and what it means. I mean, is there some boundary condition at the edges where the black lines hit the...
Well, it's the same picture no matter what I and J is. I mean, the I and J is like, you can think of it as some internal index on these brains. So we specify, I mean, you can think of them as like excitations on the brain or something. So we specify some excitation I on the brain, and then it's just the usual boundary conditions that we imposed.
I'm sorry.
But I think that from the dual perspective, right? From the perspective of the dual quantum mechanics system, you can think of this I or J label as specifying a boundary condition at the end point of that interval, the black interval, right?
Yeah, we can think of this I being somewhere here, like it's some right, operator.
Right. Isn't that what, Shiraz, is that what you were asking?
I suppose that's what I was asking, but I wanted to understand how that translated to a state of the brain.
Well, it's sort of a formal thing. Like, I mean, we're saying that suppose there is a boundary theory like this, which has this structure, then we just, I mean, there's some flavor symmetry, there's some operator which specifies the flavor of this brain.
Yeah, let me say one more and then I'll stop. Because specifying the boundary condition at the top and the bottom is essentially a way of specifying the states of the boundary theory, right?
Yes, that's right.
Okay, so I understand that you're trying to compute a path integral. You might be trying to compute a path integral for some particular final state and some particular initial state of the boundary theory.
Yes.
Okay. Now that has somehow been translated into some state of this brain.
Yes.
And I wanted to understand the logic for that.
Well, what I was saying was that the path integral representation of any of these states would take the following form, where there is some operator insertion at this point which specifies what the index is. Since we're using this flavor symmetry, like they all look the same gravitationally.
I see. Is there an assertion that the number of states in the Hilbert space of the boundary theory is the same as the number of states on the brain?
No, it's a free parameter.
It's a free parameter. So then doesn't it sound like too much to be able to specify? So there could be many, many more states on the brain than there could be in the boundary theory.
Yes. Well, I mean.
So then you shouldn't be able to create all the brain states by starting with some path integral for the boundary theory, or should you?
Well, so that feature can come out in a very indirect way. Formally, we can specify in the path integral as many states as we like. When we'll compute these overlaps, we'll see that what's really happening is that the boundary theory is an ensemble over different theories. And so in the end, the size of the relevant Hilbert space will be finite. But
just going to the next transparency, you've got a formula which says that
Yes.
This overlap, I presume, for any given brain state is given by this path integral. Is that formula meant to be literally true, or does it come with some caveats? Or?
If I really want to say what it is, then it's this. Like it's an ensemble average over the overlap.
Oh.
Yeah.
Okay.
I was sort of
thank you.
like
yeah. Okay. Fine. Thank you.
Wait. Now I got confused. I mean, okay. First of all, you must go on. But first of all, I mean, the I and the brain labels just go along for the ride. I mean, they don't affect the gravitational part of the calculation, right? If I understand. So in the end, at 0th order, the two different values of I are orthogonal to each other at 0th order.
So that
positive because the line runs through, huh?
There's a caveat to that. So that's why I put this overline, because that's not exactly true. As Shiraz was pointing out, like you can't just have arbitrarily large number of these labels.
Yeah, I agree. But at higher orders, you see some non-overlap or something. Is that right?
You don't need to go to, well, maybe, yeah, you could call it higher order.
I mean, I thought those were the rules of the game, that the brain index had to just go through continuously at some leading sort of order. Is that not right? I mean,
so even at leading order, well, it depends on what the parameters are. But suppose we computed something like the ensemble average of this quantity squared. Square was outside. Squared this average, you'd see that these states are not they don't have zero overlap with each other. They're not orthogonal, because you'll find some non-trivial overlap from these. The thing that's happening in this above calculation, this one, is that extra term, which like Shiraz was calling like the suppressed term, like delta or something, just averages to 0. So we don't care about that term, because in the average it goes away. But when you compute something like the mod square, then it doesn't. And depending on the parameters, that could be leading order. Like that could be a huge number.
No, what I mean is, I can at least conceptually, you must go on, but I can at least conceptually understand a statement which says, look, we started in some leading gravity description thinking you have so many states, but corrections tell you they're not orthogonal. But if you're going to start by saying you're computing an ensemble average, then what is the ensemble? What does that statement mean? What's that second line in your slide? Sorry, when you say it's an ensemble average. So you start with the first line, which is presumably a pure state. Psi B R1 R2 is whatever you wrote down. Is that correct?
So this calculation is independent of this state at this point. Like this is just a calculation in this model. Even before we entangle it with something else and so on. Like if I just wanted to compute overlaps in this model, this is the rules for the game. And if
sorry to interrupt, but is the statement at least that the black hole is a quantum system with internal states Ij?
Yes.
Okay, and then you take that black hole and you entangle it with the radiation to construct your first line, right? And then is the statement that you don't have a well-defined inner product in the quantum system of the black hole, and it has to be thought of as an ensemble average, or what?
Yes. Yeah, so you do, for each instance, there is a well-defined inner product and so on, like all of that is fine. But everything that the gravity path integral computes for you is an ensemble average over some ensemble, over some very specific ensemble. So any calculation that you rely on gravity for will give you an answer that's consistent with the ensemble. But on the boundary, it makes sense to ask this question, and it has some answer. But it's basically, so if you picked a particular instance on the ensemble and you wanted to compute, say, psi I1 J1 overlap with psi I2 J2, you'd basically get something like, say, delta Ij plus some corrections. And those corrections are erratic. And so when you ensemble average, that goes away, and gravity captures exactly that feature. It captures the feature that you should get delta Ij and all the other things should vanish in the ensemble average.
Okay.
And in addition, these states I, J, etc., they're also like they're also defined by an ensemble average over like coefficients in some superposition.
Yes.
Right? They're like some typical states which are ensemble averages of energy eigenstates and so on.
Yes, that's right. Yeah. So there's also a random matrix dual to this system, like once you couple it to the end of the world brains.
Okay.
So every that we'll compute will be an ensemble average. Yeah, sorry, Shiraz.
I'm sorry, Onkar, just one quick question. This question of why the boundary conditions at the ends of the boundary translate into the state of the brain.
Yes.
Do you have something? I mean,
yeah. So
why is that? Why does that happen?
Well, just by calculation, the way it proceeds is that these states psi I j are defined by like random superpositions of energy eigenstates. So there are some coefficients in the superposition, and those coefficients are also averaged over. So when you calculate the ensemble
average over in the matrix model.
Yes.
Yes, that's right. In the
okay,
dual.
Yes. Okay. Fine. Yes.
And when you calculate these averages, what you can do is you can once you do the average over these coefficients in the superpositions, this prescription naturally falls out, that you have to contract these ij indices along the branes and then sum over all the geometries. So in other words, what I'm saying is that this prescription can be derived starting from the fact that the psi I states are defined as some Gaussian random superpositions of energy eigenstates.
I see. And then the fact that these guys are some Gaussian random superpositions, not some orthogonal basis, also allows for them to have not exactly delta ij type.
Correct.
I see. Okay, thank you so much. Thank you very much.
I mean, it can be derived, but the statement that gravity is doing this is posited, right?
No. You can show it. It's similar to Saad-Schenker-Stanford. Like in Saad-Schenker-Stanford, they showed that there's a specific like calculation that JT gravity does, which is exactly the same as the random matrix model. It's the same level. Like at the same level, you can show that JT gravity plus the end of the world branes has these particular rules.
I see. Okay, you should go on. It's just the end of the world brane rules are not as clear to me. Okay. All right. Okay, go ahead to make sure the calculation is truly honest. Okay. Anyway, go ahead. Yeah.
Okay. Okay. So, okay, good. So now suppose we want to compute something like the Renyi entropies. We need to do a sum over these planar topologies. Mm-hmm. Now, this is in general a hard thing to do, even after the simplifications of like planar diagrams. And so we need some sort of trick to calculate the sum over these saddles and in order to do the analytic continuation to say, so for example, to compute the von Neumann entropy. This trick was described in their paper as it's called the resolvent trick. And the resolvent is basically some sort of generating function of these rho to the n matrices with with corresponding powers of 1 over lambda. And diagrammatically, this looks like the following. So there's a leading delta ij term, which is just represented by these index lines. Then we have some term which has rho to the first power. So we have one asymptotic boundary and all possible geometries, which is just this disk that fills it. Similarly, then we have terms corresponding to two asymptotic boundaries, which come in two kinds. There's the disconnected one and the connected one, and so on. And so forth. We'll have to sum all the way up to infinity. And this is not a very convenient way to sum it. So instead, you choose a different way to resum these contributions. And that contributions can be resummed in this way, where we just focus on what the first connected component does. So in the delta ij term, we leave it as it is. Once we look at the first connected component, it could have a single asymptotic boundary. So we have terms which have a single asymptotic boundary followed by arbitrarily many terms which are disconnected from it, which essentially is the same as what the resolvent was calculating anyway. Similarly, we can have terms which have two asymptotic boundaries in the first connected component. And then we have resolvents everywhere in the middle, which disconnect these two boundaries, and so on. So instead of
sorry, very, very sorry. Can you just go back to the last slide? There's just something very basic that I'm confused about. The resolvent, I can understand as two indices because it's related to a density matrix of the radiation. When you draw the picture below, you've got four indices. And just what exactly is the connection here? Sorry.
Sorry, which picture do you mean?
With two greens and two oranges in general, or what?
Oh, sorry. So
your left-hand side. Sorry for being so dumb.
No, that's fine. So each of these like is one subsystem. So each of them comes with its bra end and the ket end. So each like that's the
radiation, is it? Or each sub?
Yeah. This was R1 and R2. Like at this point, it's not. I mean, in their calculation, you just needed one subsystem, but I've artificially split it into radiation 1 and radiation 2, and so you have these two lines for each of them. So it's the density matrix on R1, R2.
Okay. Okay.
And then it's the same everywhere else.
And how is this connecting to the gravity side? Meaning the gravity theory has one end of the world brane, okay, with two indices, I suppose.
Sorry. So here we're computing.
Go ahead.
We're computing moments of the R1, R2 density matrix.
Okay.
Yeah.
And taking that entangled state you began with, huh?
Yes. So we're computing all of this in that specific state.
Okay.
Sorry, Pratik, this Ij are the indices on R1 and R2 respectively, right?
Yeah. Sorry, that was not clear. So this Ij is I is actually I1, I2, and J is like J1, J2. So this is like on R1, this is on R2, and so on.
Okay. So delta Ij should be
Delta Ij is really delta I1, J1, delta I2, J2.
okay. Yeah.
Sorry.
Sorry, is it delta I1, J1? I mean, or is it like delta I1, I2 times delta J1, J2?
So what I was saying was this index is, sorry, I should write this. This one is I1, this is I2, this one is J1, this one is J2. So I was saying this contraction is essentially delta I1, J1, delta I2, J2.
Yeah, this is a bit confusing because your green was I and yellow was J before.
Yeah, I think your the left labels should be I1, I1.
Sorry, yeah. Sorry, to be consistent, I should have said that. Yes.
Not only that, the range of I and range of J are different. So there cannot be delta I1, J1.
No, here he changed notation, Gautam.
Change notation, sorry. Now it should be fine. Now are you happy with this? So this would be I1, J1 and I2, J2. This would be delta I1, I2. Yeah, sorry for changing notation.
Yeah, now I'm happy. Yes.
Thanks for that. Yeah. Any other question about this? Okay, good. So now that we've resummed, so now we changed the way in which we were doing the sum. Earlier we did the sum over the number of asymptotic boundaries. Now we're doing the sum over the number of connected components in the first number of asymptotic boundaries in the first connected component. This is a little more convenient because each diagram essentially comes with a power of Zn, which is the partition function with n asymptotic boundaries. So that's this term. We have correspondingly powers of R. So with one boundary, we have one R. With two boundaries, we have two Rs and so on. So there's an R to the n. And for normalization purposes, there are these powers of K and Z1. But anyway, what we've done is essentially written R in terms of R. This is basically like the Schwinger-Dyson equation. And so we need to solve this self-consistently. Once you solve that, we can obtain all we need. But it's still not simple because we had Zn there, and it's not so easy to sum over Zn. But what one can do is use this integral representation. So there's a nice integral representation for Zn, which basically is an integral over the density of states of the black hole and the corresponding Boltzmann weight factor. But basically, once you use that, you get a nice integral equation which can be solved to get the resolvent. Okay. So what do we do with the resolvent? Well, once you have the resolvent, we just take the discontinuity on the real axis. This is something like the optical theorem. So once we do that, we get the density of states. And there's two ways in which we can do this calculation. First, we can consider the gravitational system to be in the microcanonical.
And just say once, this is the resolvent again, or what? Just say once. Sorry, I haven't quite.
This
It's
is
not
the
the resolvent which gives you density of states in random matrix theory, is it?
well,
What is lambda here? Sorry, I should have understood this better.
good. So this, I mean, here the thing we're summing over is it's the moments of rho R1, R2.
It's the moments of rho.
And so in the end, what we'll end up from this is, so lambda you should think of as the eigenvalues of the density matrix. So D of lambda will be the density of eigenvalues of rho.
It's not the Hamiltonian, but it's the density matrix. I mean, not it's the analog of the Hamiltonian random matrix. Okay,
That's right.
I see.
Sorry, and in between, your original R had indices Rij.
Yeah, good. So I did this trace here, and this is what I'm defining as R.
Okay, thank you. So if you go back to your original definition, once you do the trace,
Yes.
you get the right hand side rho is replaced by traces of rho to various powers.
So it's the generating function of trace rho to the n. That's right.
And when you take the pole, you took the pole with respect to lambda, right? Sorry, what when you computed this D?
Oh, the spectrum.
Yes.
Yes. So we have R of lambda. It's the discontinuity in R of like lambda on the real axis, above and below the real axis.
Okay, and if you could go back, I'm very sorry, but go back to your definition once again. The definition of the resolvent.
Yes.
And so if I computed this discontinuity, what would that be in terms of this rho, please?
So another representation for this is this basically is like the identity over lambda minus rho.
Exactly.
It's like lambda minus.
Right. It's wouldn't your discontinuity be the number of or the density of eigenvalues of rho at lambda?
That's right. That's exactly correct.
I understand. Yeah, fine. The spectrum.
It's the spectrum. Yeah.
Right.
Of rho. Right.
Good. So once we compute the resolvent, we can compute the spectrum, and then from the spectrum we can obtain all sorts of quantities like the von Neumann entropy. There's two ways in which we can do this calculation. One is where you have the gravitational system in a microcanonical ensemble, so you're using fixed energy boundary conditions, or you can use the canonical ensemble where we have like fixed temperature boundary conditions. They both have nice forms. So the microcanonical ensemble is actually identical to a random bipartite state. So it's literally what Page computed. And it has a sharply peaked density of states near one particular eigenvalue. And on the other hand, and this is analytically tractable, by the way. The canonical ensemble is hard to get analytic traction over, but what we can do is compute it approximately. And there's also a nice answer for what happens there. The interpretation is that we have a thermal spectrum for the black hole, which gets cut off because of the effects of the brane. And it gets cut off by some value that's determined by where you are at the Page transition. So far on one side of far before the Page transition, you have something like a mound of eigenvalues. But as far on the other side of the Page transition, you expect to have the entropy of the black hole. And so this cutoff thermal spectrum is some sort of intermediate which interpolates between these two and can be used to compute details of the phase transition.
Pratik, there's something, again, I'm not quite getting in my head. Where are you putting in? So let's say this is modeling a black hole which is evaporating, radiation is coming out, you're computing, I understand the features about the density matrix, its eigenvalues and so on. But are you looking at all the radiation that has come out up till some time? Part of it, where is that information about how long you've waited or the part? I'm not quite sorry.
Yeah, no, that's a very good point. So in this model, there were essentially two parameters, right? There was S0 and there was, or like beta, like these two parameters, and K, right? K is the number of flavors. So the way we can think about this is, let's say you waited a time such that you collected K radiation modes. And so they're entangled with the interior modes, which have similar dimension of the Hilbert space being K. And hence, so what we're saying is once you wait for that, then you collect all the radiation and put it into this R1, R2 system. And so we're at that time. Now, depending on what K is compared to S0, this could be post-page or pre-page. So as you tune these parameters, you can see the phase transition.
Okay, yeah, this has to be explained every time to me by Omkar also. The end of the world brain is another way to say that these are the Hawking partners that have gone in.
Yes.
More or less, right? So you're actually changing the number of internal states, roughly speaking, as a way of keeping how much radiation has come out. Huh?
Exactly.
Okay.
Exactly.
Okay.
And sorry, and is there any 1-2 so far? In your calculation, was there any 1-2?
No. So the only reason I introduced the 1 and 2 was because it'll be useful for the reflected entropy calculation. It doesn't make any difference in the entanglement entropy calculation.
Right. It's everything is in terms of this one parameter K, which counts the total.
Exactly. That's right.
Okay. Thank you.
Thank you for that. Okay, good. So yeah, here's the spectrum. This is all computable. We get
Sorry, Pratik, for being constantly disruptive. When you say you can calculate in microcanonical and you can calculate in canonical, I'm trying to understand that. So at the moment, you've got some spectrum as a function of lambda, which I suppose you call a microcanonical.
No. So what I was saying was, so we had some integral equation that we got here.
Yes.
All of this was, I mean, this was derived using the canonical anyway. But once you have this integral equation, we can try to solve for R self-consistently, like solve this equation for R. That gives us some R of lambda, and then we can use that to get D of lambda. That's what I meant by solve. On the other hand, like there was a simpler thing we could have done, which was we instead of having Zn defined by the canonical ensemble, we could have defined it using the microcanonical and done the same sum, and we would still have this Schwinger-Dyson equation we're solving for. So we self-consistently solve for R and obtain the spectrum for it.
I'm so sorry. Let me just understand even canonical, microcanonical. I'm not. I thought you had a particular state of your black hole, which was end of the world brain correlated with some radiation modes. In what sense is this either canonical or microcanonical? I mean, why are you using these words?
Yeah. So the reason I'm using these words is because I really tell you what psi ij was. When I said psi ij, it's like it's some state of the black hole system with these brains with brain flavors I and j. But what boundary conditions I used to define psi itself was left open at this point. So there's a choice that you can make, and two nice choices are the canonical ensemble, where we fixed these fixed length boundary conditions, or we could also use some fixed energy boundary conditions. These are just two different calculations. They would be two different states.
Could you just say for a minute what in the calculation how it affects?
The way
as far as I could see, psi ij was some abstract states on the end of the world brain. I don't understand what you mean by the states are fixed by. Yeah, so please tell me a little.
Suppose so let's first focus on psi ij, where we've defined psi ij using the canonical ensemble.
I'm not understanding the words.
So we
define psi ij using canonical.
Define psi ij with the boundary conditions fixed here, which was we specified the flavor of the brain, and we specify that this boundary has a renormalized length beta over 2.
Okay. Yes.
Good. So that's what I'm calling the canonical ensemble. Alternately, what I could have done was define this boundary to have boundary conditions given by a fixed energy instead of a fixed renormalized length.
I see. Thank you. And so the easier, in path integrals, the easier thing to do is to fix the length of the boundary. Yes. And then you can do a Legendre transform of that.
Absolutely.
Okay. Thank you so much.
But sorry, Pratik. Since Shiraz asked this question, which I also then realized I hadn't understood. But so, okay, I get it that you can take the length or its conjugate or whatever energy. But if you're going back to the physical question of a black hole evaporating, K, I agree, okay, stands for how much radiation you gathered. But the temperature of the black hole is, of course, changing in the course of evaporation.
So as I
what is the, what choice do you make? I mean,
as I said before, like the beta here is also a parameter in the problem. So we could start with so you could give me your favorite black hole, start with whatever temperature you like, let it evaporate for whatever time you like. Once you give me all of that, I can extract the relevant radiation, put it in a different system, and that fixes my parameters beta and k.
But I mean, is beta supposed to be an average temperature of all the radiation gathered? What is it supposed to be?
It's the temperature of the black hole that's remaining.
Of the black hole that remains, is it?
Yeah. Yes.
It's the temperature of the black hole at that time, after it's emitted all.
Here, at that particular time, we're separating the radiation and giving you this black
time. That's right, Shiraz. Yeah. At that time, the black hole has some internal states which correspond to the Hawking partners that went in, that equal the total number of states of the radiation. But then you have the black hole with those states, and then you compute whatever with that black hole at that temperature.
Yes.
Okay. Thank you. All right. Good.
So having said that, so what I wanted to emphasize here was that we have these two interesting spectra which we get, and then this can be used to compute whatever function we'd like of the eigenvalues. So for example, any Renyi entropy or an entanglement entropy and so on. Good. So having set up all of this, let me start with the calculation that I actually did. So now let's do the same thing for the reflected entropy. So as we were talking about previously, there's a path integral way to think about this. Instead of preparing the canonically purified state, what we'll do is prepare the state, which is rho to the m over 2. And now we've split this into R1 and R2. So you can think of this as the A and B that we started. For any even m, this can be prepared by the path integral. Once we do that, what we want to do is extract the R1 star spectrum. We want to compute the entropy of R1 star. So we extract the spectrum, and then we can do that using the resolvent trick, very similar to what we did before. Then eventually we just analytically continue to m going to 1. The analytic continuation will be simple, like it won't require any extra tricks. And this will give us the reflected entropy in the same model. Now, what's the answer we even expect? Well, as we saw before, there are two phases. So the disconnected phase for the radiation is where it doesn't have a non-trivial island. And so in that context, the R1 and R2 systems are as good as separate, and there's no cross section that you need to split them. So the answer is 0, as we expected in the holographic case. In the connected phase, the radiation has this island. So this brown shaded region is the entanglement wedge of R1, R2. So now you have this non-trivial entanglement wedge. So you need something to split these two systems. And sort of by a quantum generalization of what we discussed before, you can argue that it's going to be the minimal value of either log K1 or log K2. So a way to think about this is log K1 is just the entropy of the A system, and log K2 is just the entropy of the R2 system. And what we're doing is basically cutting the state at either R1 or R2. And this is analogous to the entanglement wedge cross section. So we'll have, and I'm sorry, I should have said it's twice of this, because the answer for the reflected entropy is twice the entanglement wedge cross section.
Yeah, sorry to back you up. But yeah, disconnected phase, I understand why the radiation has 0 entropy. And then you divide it into two parts, R1 and R2. And of course, both of them will have the same entropy each. But then you construct the reflected entropy, say R1 star, I guess you call it. And that has some entropy because A is entangled with B and A star with B star.
Yes. So
it's twice the entropy of A, right? That's what you'd get.
It'll be twice of the smaller one. Yeah.
Oh, okay. Yeah. Sorry. Yeah. Which will be the entropy of A or B in the first case, disconnected phase case, right? Am I thinking right?
Yeah, that's right.
Okay, okay. And then you go to the connected phase, and there, of course, rho AB is a mixed state. It has some entanglement, and then you do the same thing, and you try. Okay, go ahead. And now you're going to give us the description of the reflected entropy in this case, say.
So the reflected entropy in this case, as I was saying, was so now that you have this geometric connection, so there's this non-trivial entanglement wedge connecting R1 and R2. So we can think of it just morally as R1, R2, and there's some geometric connection which connects it to the black hole, and there's some here. There's actually no geometric surface that splits these two systems because both of them are right on the brane. And so the only possibilities are having sort of an entanglement wedge here or here. So it's sort of like cutting the R1 leg or the R2 leg. This is sort of, I'm just drawing like a network picture for the geometric description.
Okay, so you're going to cut your end of the world brane, is it?
Basically, so we're not like we're not cutting it geometrically, but like abstractly. There's like two Hilbert spaces living on the brane, and we're splitting them. Yeah,
I see. Okay, go ahead. I think you'll describe this more. Yeah.
Sorry, Pratik. How do I know that when there should be zero and when it should be that the non-zero?
So as we saw in the previous example, like the only time when you need an entanglement wedge cross section is when you do have a geometric connection between these two systems. And so the disconnected phase here is basically when the R1, R2 system doesn't have an island. It doesn't have a region associated to it.
How do I know that? I mean, island is some different thing having to do with entanglement entropy, right? So why is this also detecting this tripartite system?
Okay, good. So that's exactly, so that's a very important point. So let me go back to the holographic example. In this example, the island, the analog of the island is the entanglement wedge, right? So the blue region here. The existence of a connected phase for the blue region guarantees that you have an entanglement wedge cross section splitting the two regions. So the connected and disconnected phase, when we talk about it in this context, is the same as the connected and disconnected phase of the entanglement entropy. So the same condition dictates it, but the value is different.
Okay. Yeah.
Okay.
Should it not? Yeah. Okay. Fine.
Okay. Good. So now let's go back to the diagrammatics that we did previously for the entanglement entropy. It's quite similar. So let me just show you the pictures. When we prepare rho to the m over 2, it looks like the following. Initially we had prepared rho and it had one asymptotic boundary. So now when we have m over 2 copies of it, we just glue together m over 2 copies of it. And then we have that many asymptotic boundaries. So in this case, we have 4, m was 4. So m over 2 is 2 and we have 2 asymptotic boundaries. Then we consider a particular involution of this. So we just consider this rho to the m over 2 gamma, which will be a basic ingredient in this calculation, where all we've done is moved the green label from the right to the left and the orange label from the left to the right. This is just some trivial operation that we're doing abstractly. And this purple line is just representative of everything in the middle, which is m over 2 asymptotic boundaries glued together. Okay. Now, if we take this and its conjugate, so the conjugate would be the same, but with the orange and green flipped, then what we get is when we multiply these together, we get one copy of rho R1 star. How do we see that? Well, this you could think of as the state rho to the m over 2. And then we want to trace out R2 and R2 star. What that needs is an index contraction of these orange indices. So that's what we've done here. And then we're left with a density matrix on the two indices that are left, which are R1 and R1 star. The same on this side. So this is just the bra and ket part of the density matrix.
Sorry, is this for m equals 1 or?
This was m equals 2, but this purple line is supposed to contain m over 2 boundaries. So I'm just using it as shorthand. Okay. This itself contains 2 boundaries, or like m over 2 boundaries in general.
And Pratik, you said this, but you've taken the brane indices and divided them into 2 sets?
Yes.
One of which is entangled with the first part of the radiation, and the second is entangled with the second part of the radiation?
Yeah, it doesn't really matter. We're taking this entire state to be maximally mixed anyway with the radiation. So yeah, but yeah, some part of the radiation.
No, I didn't understand. I thought 1 and 2 were states of the radiation. I want to understand how that translates onto the brane.
Well, they're the same index. So we use this state. Where did it go? So we use the state where like the labels on the brane index were the same as the labels on the radiation. So whatever calculations we do, I mean, it's whether we think like the radiation labels or
are these states on the? Is there some orthogonality of these states? These psi ijs?
There's an orthogonality on these states. There's not necessarily an orthogonality on these states.
Okay, so the states on the branes that are in 1 and 2 could be could be overlapping.
Yes. Yes.
So then I'm not understanding. I mean, what the rules say? That you're supposed to sum over these states even though they're actually the same state. I mean, it could be that the one component is entangled with the same brane state as the 2 components. Sorry. So, yeah, what I suppose I'm misunderstanding is that there's a product here. So I'm sorry, it's an ill-formed question, I suppose. You've got these one part of the radiation state and the 2 part of the radiation state, and the radiation is a tensor product of 1 and 2, I presume, right?
Yeah, that's right.
And now you are somehow using that tensor product structure to make tensor product structure on the brane, on the Hilbert space of the brane, or not?
We're not necessarily, so I'm being agnostic about what the Hilbert space structure of the brane is, but I'm just saying that in the path integral, we can represent the brane by flavors. And those flavors are...
By what, sorry? By flavors, yes.
Yeah, sorry. So, and these 2 flavors, like one of them is this green flavor index and one of them is the orange flavor index. The green one is entangled, is such that we're preparing this state. So I'm not, maybe I shouldn't say entangled. So I'm saying I'm preparing this particular state and I'm being agnostic about whether these states are orthogonal. But this is the particular state I'm preparing where the green index on the brane is the same as the R1 index and the orange index is the same as the R2 index.
But this is not meant to denote some tensor product of the brane state into I1 and I2. I1, yeah. I2 and J2. No. So I and J are just a compound label for the brane state.
That's right. Yeah. It's just helpful for diagrammatics, and I want to keep the R1 and R2 coupling separate. So that's why.
R1 and R2 coupling separate. But it's just IJ is a composite label. There's no way of separating psi IJ into...
There's no way to separate psi IJ, but there's a way to separate R1 and R2 into I and J. So
correct. That's fine. But psi is just psi IJ.
Psi is just psi IJ.
So these dotted guys I should think of as coming together. There's no meaning to I2 without J2.
That is correct. So in the end, the answer you'd get is like, if you take I and J to have too many labels, which like crosses the black hole entropy, then psi IJs will have significant overlaps with each other. And there's no meaningful sense in which these I and J are orthogonal states. That's correct. For small enough I and J labels, they're approximately orthogonal. So there is a nice distinction where like these really...
At the moment, I'm not seeing how this splitting into 1 and 2 can ever enter your calculation. Because if I2 and J2 are just completely, some bound index, if it's just a matter of terminology. But you'll come to that, I suppose.
But I don't see why. I mean, on R1 and R2, they're separate though. So I don't see.
R1 and R2, they're separate. But I thought in the sum over I and J, that will always give you sum over I times sum over J will be K, right? There's no way you can sum over I without summing over J.
But I have these 2 R1 and R2 systems in hand, and I can measure which labels are I and which labels are J.
Okay, what I'm not understanding is I thought that psi ij was labeled by both indices I and J. together. There's no meaning to saying one in psi ij without saying also two. Right? I mean, you're labeling your state on the brane by both indices. You're saying it's whatever is correlated with 1, 2.
So yes. And what I'm saying is, I think your objection was that these are not orthogonal states. And I think that is all. So what I'm saying is, not integral, there's a well-defined way in which I'm specifying what the values of these brane indices are.
Okay.
However,
it's wonderful. I just want to see how you use the split in your calculation.
Okay, sure.
Yeah, I have the same question, because ultimately you'll do a gravity calculation to implement your cross-section or something, right? I don't know. Okay, let's wait and see.
Okay. Okay. Good. So at this point, the way okay, maybe I should just check if this is clear. So at this point, the way I'm separating the I and J indices are there's just some formal indices that are labeling these branes in terms of the green lines and the orange lines.
Yeah.
Is that?
And the green lines and the orange line should be thought of as a composite set of lines. Because psi is labeled by both indices I and J. You're repeatedly saying it's not a product of a state associated with I and a state associated with J. So I can't split those indices.
That will be an outcome of this calculation. I mean,
no. Why is it an outcome? You have to say what psi ij is. Either it's a tensor product state or it's not. If it's not, you cannot split them, right?
Okay, good. So if you want to say that, then okay, fine. So let me say this. Maybe this makes you happy. So I don't, at this point, I'm being agnostic about what the boundary theory is. I'm just describing everything in terms of the gravity path integral. In the gravity path integral, there's a very well-defined sense in which I can split these I and J indices. It's my choice. That's my definition of the model. However, what I want to say is an important feature of this calculation is that the boundary theory is an ensemble average. If you were to pick a particular theory, then I and J indices wouldn't make sense because they aren't separate, as you're saying. But in this ensemble averaged calculation, there is a well-defined sense in which I and J make sense. It's because of the path integral.
Wait, so you are saying that these I and J indices can be split? So can you make that statement precise? Is that because the state on the brane is a tensor product of an I state and a J state? Is psi ij a tensor product state? In what sense can it be split is what I want to know.
I don't want to use tensor product because I'm not really using a Hilbert space description for the branes at this point.
What does it mean that they can be split? What does it mean that these indices can be split? On the brane, I don't mean about the boundary.
We're just defining the path integral to have these two flavors of the branes as boundary conditions.
These two flavors, and but if there isn't a separate Hilbert space associated with, I cannot understand what those words mean in context.
Okay. So should I read your question that why is it that the path integral is proportional to delta I1, I2, delta J1, J2?
For instance.
Okay, good. So this was something we saw earlier, right? Like so if I computed psi I1, I2, I1 J1 and psi I2 J2, then it is proportional to delta Ij.
What do you mean it is proportional? That I mean, suppose the state proportional to 1, 2, entangled with 1, 2 was the same as the state entangled with 1, 1. Then it would not be proportional.
So at this,
it is proportional. I cannot understand those words.
Well, so there's a well-defined way in which I can calculate this object from the path integral. And in that calculation, it is proportional to delta Ij.
How can you calculate it when you don't, if you know nothing about
taken to be proportional?
Sorry? I missed the question.
I think Abhijit saying is you're asserting that it is delta I1, I2, delta J1, J2. It could have been or may not have been, right? How do you know?
Absolutely. It could have been or may not have been. That's correct. What I'm saying is when you do this gravity calculation, we see that it is delta Ij because these brane labels are identical. Now, this is in tension with the other issue that you pointed out, which was how is that possible? Like, how can you just arbitrarily increase the number of labels?
I'm sorry. So before you get to that, I cannot see the first part also. When you do the gravity calculation, where in the gravity calculation are you putting in these I and J? This is some I and J were some abstract things, right?
Yes, they are.
Yeah, but these states in the boundary quantum system are defined by, as we said before, these random superpositions of energy eigenstates. That the coefficients of those random superpositions have these labels I and J on them, right? And so I think this is being put in by like the distribution that you're choosing to average these coefficients over. Is this correct, Pratik?
Yes, that's right.
I see. I see. Sorry to interrupt, Onkar. And so these I and J should not be thought of as states of the radiation?
Both here. So I and J here are the states of the radiation as well, but we're also using it to label the states of the brane, which in this dual description are these random superpositions over energy eigenstates.
No, but the way Onkar was saying it, it sounded like the states of the matrix model, which was dual to the JT gravity, right?
Yes, that's correct.
But in addition to that, there's radiation, I thought.
Yes,
that's
yes.
So then I'm not understanding. Are they states of the radiation or states of the...
So I and J label states of the radiation where they are orthogonal states, but on the matrix model, which is dual to JT gravity side, they also label some kinds of states. Okay, and there they label these random superpositions of energy eigenstates. Okay.
And sorry, Onkar, why is there a one-to-one correspondence? Why is this double thing happening? Why is the state of the radiation also a state in the boundary?
It's a choice, right? I think it's a choice that Pratik has made.
Sorry, Shiraz, I mean, the coefficient of Ij radiation is defined to be psi Ij, right?
Yes.
Yes.
One way to say it, yes.
Let's say we have that.
And maybe Pratik, maybe it would help to like just clarify the definition of psi Ij in terms of these superpositions. That probably will clarify things, I hope.
Maybe we can postpone these this discussion for now and let Pratik go on.
Yeah. Sure.
How do you feel?
No, we must let him go on. But just this thought is Pratik about the gravity integral. As per the rules you are using for the index flows, you will get this delta Ig to begin with, right? I mean, that's the zeroth order. Just from the purely gravity side, how does it happen is the zeroth order thing, right? So, okay, anyway, but go ahead. And then, of course, there's a random matrix interpretation, but what you're using is the gravity calculations here, I think.
Yeah, I'm only using the definition using the gravity path integral. All calculations just rely on that.
So I think if you clarified that calculation, it would help everyone in terms of how it's working. Not right now, but whenever you discuss it.
Yeah, I think Pratik, you should go ahead. I think, and maybe we can get back to these issues at the end.
Okay, good. Okay, so where was I? Okay, good. So going back to the reflected entropy diagrammatics. So now what we're using is this basic ingredient where we have these m/2 asymptotic boundaries, which have these two green index lines, which correspond to the state on R1 star, and these two on which is, well, maybe this is confusing. So maybe I should say this is precisely, it's entangled with the states on R1 and R1 star, like the radiation. The index is the same, like whatever index, if you have some index I on R1, then you have the same index on this brane. That's what I mean by the state on R1. Okay, good. So using two of these, we now trace out this R2 and R2 star. So that just implies we have two copies of this and we glue together these orange lines as such and getting a density matrix on R1 star. Okay. Now we consider a slightly more general version of the resolvent. We consider R of lambda, where we take rho to the m/2 with these gammas, with these involutions, as the off diagonal elements, raise them to the power of k, and then sum over this index lambda. At this point, this doesn't necessarily have any meaning, but it'll be relevant for the reflected entropy calculation. How is it so? Well, if you look at this, like each time you take two powers of this off-diagonal matrix, you'll get diagonal components that essentially are rho R1 star to the power of n and rho R2 star to the power of n. An example of this was the thing we saw in the previous page where the multiplication of these two elements just gave us rho R1 star. Okay.
Sorry, Pratik, what is this symbol gamma plus? What is this?
So this gamma was just, it's just a formal statement. What all I mean is that I'm taking the green. So here we had these green and orange indices on one side. All I'm doing is taking the green index from this end to the other side and the orange one to the other side. That's all I mean.
Okay.
It's just a formal like transposition.
Okay.
So Pratik, there should be some power n by 2 or n there on the left hand side in the last line.
Over here.
No, in the previous slide, the last equation, the left
This
hand
one.
side.
So how I'm defined this. So this is the density matrix in the state rho to the m over 2. So
okay, fine. Yeah, that's the one. So you just take n to 1. That's the point.
Yeah, eventually I'll just take m to 1. Yes.
Yeah.
That's right. Good. So now this matrix resolvent has diagonal components that are relevant to us. We want this rho to the power of n for R1 and R1 star. And so this is the generating function of such density matrices. And then eventually what we'll do is look at the 1, 1 component. So that picks out this R1, R1 star, do the trace. And so this object is now the same as the resolvent that we had before. It's the generating function of trace rho R1, R1 star to the n. Once we have this particular component of the resolvent, we can do the same thing again and get the spectrum. So it has the same relationship to the entanglement entropy calculation as the usual resolvent. Okay. Good. So how do we calculate this? Well, I won't go into too many details. I'm already way beyond time. So all I'll say is that the diagrammatics is pretty similar. What you do is just sum over all of these components. There are different kinds of diagrams. There are these disconnected diagrams and connected diagrams, and it's similar to the previous resolvent. One thing that I'll point out is there are two classes of diagrams. So remember that this purple line itself contains m over 2 boundaries. So these m over 2 boundaries are split into these black boundaries here. So I'm explicitly writing them all out. And this is just a heuristic for saying that these are disconnected boundaries. So for example, we can have something where these two boundaries are connected, but they're disconnected from the other group, which is these two boundaries. That's what this representative means. Now, this diagram, if we just trace, so all the orange loops have been traced over. So they just form closed loops. For example, this closed loop. But we can look at what the green lines are doing. So the green lines are so and so. So they look like this particular form. So they're proportional to a projector. It's a projector which basically sets the indices on R1 to be the same as R1 star in the bra and the ket separately. You can think of this as it's basically a particular state. Similarly, the other diagram is the connected one. And in this, we'll have a different kind of contraction. So if we trace the green lines in this diagram, we have something of this form, and the green line goes this way. So if I straighten it all out, it's basically a state which is maximally mixed. So how do we see that? The density matrix of R1 and R1 star here will take the form where it's basically maximally mixed on R1 separately and R1 star separately. They're basically decoupled from each other and both are in a maximally mixed state. There are essentially these two kinds of diagrams. Okay. Good. So the trick now, so initially also we saw in the entanglement entropy calculation, the resolvent sum is hard to do as is. We'll have to use some trick to resum it. And the trick is the following. It's very familiar from QFT, I guess, where we consider 1 pi diagrams. So this is very similar to that, where we consider sort of the connected part of the resolvent, and we use this F to denote this connected part, and the resolvent is then just given by a sequence of pars of these F. So it's like gluing together these 1 pi diagrams together to get the full propagator. Okay, so these Fs also take a similar form, but now there's an interesting thing that shows up. The Fs consist of diagrams which are, for example, connected between boundaries, but we can now insert arbitrary number of boundaries in the middle. We want some connected component which connects the two endpoints, but in the middle, we can have arbitrarily many asymptotic boundaries. And this is now similar to the entanglement entropy calculation. So what we've done is expressed F in terms of R, whereas R itself was expressed in terms of F, right? So we have some sort of self-consistent equation again. I'll pause for questions if there are any.
Go ahead.
Okay, good. So now we have some sort of a matrix version of the Schwinger-Dyson equation that we saw before. There's R that's expressed in terms of F, which itself is a function of R. So we have a matrix equation for R. We saw that the resolvent that we care about just is some particular component of this R. So solving for R will give us the relevant spectrum. So we can solve for this self-consistently. There's one assumption that comes in at this point. It's hard to solve it to all orders, but we can do it order by order in the size of the connected component. So what I mean by the connected component is here, the size of the connected component is just one. There's just one purple boundary to which this gravity saddle is attached. And here we have two of them. So this is the one with the size of the connected component is 2. And so on. What we saw was that the effects of anything beyond k equals 2 was irrelevant. It didn't affect the answer much. And further, this was very consistent with what we got from our numerics. So this is an assumption in the calculation, but I think it's well justified. Once you make this assumption, then you get a nice spectrum. So even if you didn't capture all the details that I just talked about, let me just mention what the result is. So the result is as follows. We saw that there were two kinds of diagrams. There was diagrams which were like the maximally mixed one, and there were these projector ones. And essentially, all we end up is a spectrum that consists of these two features. So there's a single pole, which is sort of related to the projector, which has some weight, P naught. This P naught is some function of the parameters in the problem. And we have a mound of eigenvalues. The number of eigenvalues here is min of k1 squared or k2 squared, whichever is the smaller one, with some weight p1, and they're together normalized. So we have basically a density matrix which takes this form of these two features. P0 and P1, sorry, was there a question?
Shouldn't it be that if you looked at the, let me just get my bearings. The radiation altogether is nearly pure or not? Are you way after the page time here or not?
This is arbitrary. So at any point, this is the spectrum. What changes is the weights. So see these weights P0 and P1 change as you cross the phase transition. So what I was going to say was this P0 is almost 1 when you're on the pre-side of the phase transition. That basically says that there's a pole. So the spectrum is just a pole. It's a pure state essentially. And so the entropy is 0, which is what we expected from the disconnected answer. On the other hand, P0 falls as you cross the phase transition. And so eventually the entire...
Sorry, please excuse me. I'm just trying to understand. So even when R1 and R2 all together would be pure, here you're computing the reflected entropy for R1 star, right?
So I should say again, R1 and R2 will not be pure at the early stages of evaporation. At the early stages of evaporation, they'll be maximally mixed.
Correct.
What does is because they're maximally mixed, both of them are individually just entangled with the black hole. They're not entangled with each other in any sense. So what ends up happening is that the correlation between those two is 0. And their individual, the density matrix of A star is 0. Like A is just purified by A star, not by B.
Very good, very good. So that's what I was trying to understand. So this is the statement. So when you have a single pole, that means A star is pure by itself.
Yes.
And that's the situation early on. And later on, but all I was saying was the later on should be roughly when R1 and R2 together are, nearly pure, right?
Well, I mean, they go from...
That is, they should be after the page time as far as the full black hole problem is concerned. The entropy of the, how should one say it? The entropy of the black hole should be, much smaller than the naive entropy in the radiation,
Absolutely. Yes, that's right.
Okay, and is that the case on your left then? Is it?
On my left, sorry, which...
We are getting the mound.
Oh, this one, yes. The mound of eigenvalues will dominate when you're in that connected phase. Yeah, so past the phase transition. So what happens in that phase is, so we have R1, R2, and the question is what is entangled with what? So we have B. At early stages, R1 is entangled with B, so is R2, and there's nothing correlating R1 and R2, so the cross section is 0. At late stages, this entanglement structure changes. What happens is B is entangled with both of them, but R1 and R2 are huge. So they're actually entangled with each other as well.
Right. And on the gravity side, when you do the calculation, maybe that was implicit in all your indices, but I didn't catch it. What is, the analog of the entanglement island coming up is what precisely? I mean, is it just that once you get the island, even though you're trying to cut the brane degrees of freedom, what's the interplay between having the island and trying to cut the brane degrees of freedom into two? Just roughly. Yes. That whenever you like, at whatever stage in the talk. Sorry.
I think this is a good point to talk about that. So the rough model that I have in mind is the following. So it's like where the geometric picture is rough, something at the connected phase is something like where R1 and R2 are connected sort of via the black hole. I mean, because they're in a connected phase, they contain sort of a portion of the black hole, the interior in particular. And so there's a geometric connection between them, which is split either at this point or at this point, which gives rise to this min of K1 squared and K2 squared. That's the analog of the cross section in the gravity calculation.
This line, that black line, is the end of the world brane or what? That's
not a good picture.
What you were drawing. Sorry.
Okay.
But you know what? If it's delaying, finish your talk. I mean, I don't know, because whatever you like, up to you. But I wanted to understand this. Yeah, but go ahead.
So what I mean is, so this is the region that's the interior, which is now contained in their entanglement wedge, right? So the entanglement wedge for R1 and R2 contains this region of the black hole.
That's right.
And so this, so the branes here, I mean, physically, they're just together. They're just some abstract indices on top of that. So the only way to split the branes is like either by sort of cutting the entanglement at the green, at R1 or at R2. There's no nice cross-section picture in this context because like the branes are basically sitting together.
But what does cutting at R1 mean in your picture? Just one, if you can translate it.
That's okay. So maybe this will become clear later, slightly later. I'll draw a network picture for it, and maybe that will be more helpful.
Okay. Go ahead. Please go.
But perhaps you can explain it in terms of some like quantum extremal version of the reflected entropy.
It's basically the quantum generalization of it. So if we were to, okay, so let me just say that. So if we were to generalize the reflected entropy proposal to be min, so twice of min EW plus the entropy of the region bound. So maybe I should go to the first picture, that'll be clearer. So here, if we were to generalize the entropy to be SR equals twice min EW plus the entropy of the bulk region that is here. Okay, so if you were to, it's not the entropy, it's the reflected entropy really, but there's a bulk entropy contribution coming from this region. Then you can think of this as some like quantum generalization of the holographic proposal. And what we're doing here is exactly that. So
I see, you mean you're just including the matter entanglement across your dashed line. Okay.
Exactly.
Fine,
exactly.
fine.
There's no geometric cross section, but there's a bulk term because of the entropy of the radiation.
I see. Okay, but you're doing the calculation on the black hole side, right? If I understood.
Well, so we're doing the calculation using gravity, but we're computing the entropy for R1, R2. Yeah.
No, I understand, but using gravity, when you do it, what is the picture in the gravity calculation of this cross-section showing up? Is there something I thought you were going to finally tell us that somehow you cut the brain or something. Maybe I was wrong.
It's morally that, but there's no nice gravity picture in this specific context. Like, I mean, the gravity picture you draw. So firstly, here what we're doing is doing a more complicated calculation where there's not a single saddle. There's a sum over all of these saddles. And so there's not going to be one particular nice geometric picture.
Okay.
If you were like far on one side of the phase transition, then what you could do is just look at like the paper by Datta and Faulkner. They had this path integral construction of how they got this particular saddle, and it's pretty much the same as that. Essentially, what will happen is you'll end up with diagrams which count, which look basically like this. So you'll have, after you compute everything, like after you've included all the gravity contributions and so on, you'll just have these index loops which will either take this form or this form, depending on which side of the phase transition you are on. And that's pretty much the gravity picture for it. Although I will mention some more heuristics after this, like maybe that'll help you.
Okay. These are index loops on the end of the world brain, right? Huh? Okay, I'm with you. Okay, go ahead.
So Pratik, how long? So sorry to be asking this question, but how long do you think you would need more?
I feel like I can wrap up in 15 minutes, maybe.
Okay.
Yeah. I don't know if others have like time constraints, then I could like wrap it up faster. But
no, go ahead. Take your 15 minutes. Yes.
Okay. Thank you.
We will try to resist from asking unless it's important.
I hadn't expected but this was a great conversation. Good. Okay, good. So let me just say quickly, the weights of these eigenvalues, of this eigenvalue and this mound are basically computed by a simple function of the Renyi entropy. So in particular, what plays a role is the half Renyi entropy. Maybe this goes back to a question that was asked initially. Maybe this makes some connection to that question. But anyway, this is all you need to compute to understand what happens to the reflected entropy. You just compute the weights and then the answer is pretty simple. There's a nice interpretation to this probability, which is it's just the probability of the spectrum being in the pre-page part. So in the thermal spectrum, there's always some probability of being at different energies. And depending on what energy the black hole is at, the transition happens at a different point. The page transition, because the area of the corresponding black hole will be different. And so there's some interpretation that was given in the West Coast paper for what you can think of as a pre-page probability, which is 1 when you're far on the disconnected phase and 0 when you're far into the connected phase. And that nicely captures the weight of this single pole. So it's very closely related to the fact that the reflected entropy has a transition exactly where the entanglement entropy has a transition. Very good. So once you do that, you can plot what the entropy is like. Again, we can do the calculation in the microcanonical ensemble, and it's very similar to what a random state would be like. And in the canonical ensemble, again, we can compute it approximately. There's some approximations you can use similar to the ones for the entanglement entropy. And the answer is pretty simple because we had these two sort of super selection sectors. We had these two sectors which contributed some amounts. So they have, the way I like to interpret it is there's a sum over these two blocks with different weights and different values of the cross section, which I like to call the area term, although it's some sort of quantum generalization of the area. And there's some mixing term, which is the Shannon entropy. So there's a nice feature that in the canonical ensemble, the transition is sort of spread out a little more. This is similar to what happens in the entanglement entropy. And this is a nice feature that we could see from this model. I think it's going to be universal. Good. So now that I've completed the third part of the talk, let me just mention some things I wanted to say about tensor networks, because what I want to emphasize, like even if you don't understand everything I say, what I want to emphasize is there's a close connection between the calculation I did and tensor networks. And tensor networks essentially capture all the features that you have in that model. So in the tensor network, there's a very similar picture for canonical purification. You can take two copies and then glue them together, which just are these index contractions and so on. The problem is, so naively you'd think this would just give you the same picture. Like we're just drawing the same cylinder together. We're going to use the RT formula and compute the reflected entropy. But the problem is this tensor network has these correlated tensors. So the tensors on one copy are correlated to the tensors on the other copy. And it isn't obvious that the Ryu-Takenagi formula holds once you have these correlated tensors. The randomness in these tensors was an important feature. So in fact, in a paper with Chris Akers, we showed that not all tensor networks have this nice holographic feature when you start probing these finer structures. And in fact, like in a recent paper by Omkar, it was also emphasized how tripartite entanglement plays an important role in holography. And so,
sorry, I shouldn't ask, but nice features, do you just mean if you cut along some minimal thing, you get the entanglement? Is that what you mean?
Eventually, what I'm going to tell you is that there are tensor network models where you'll get the holographic answer. So it will have the same interpretation as cutting the entanglement wedge into two parts, but not in all models. So what I'm trying to say is there are finer details that some tensor network models capture very well, not all.
Yeah.
There's still things to be learned from it. So a very general argument for this is the relation between random tensor networks and fixed area states, which were proposed in this paper with Chris Akers and also in a paper by Dong, Harlow, and Marolf. The idea is pretty simple. In holography, usually we consider path integrals where we fix asymptotic boundary conditions. And as told to us by Hartle and Hawking, I guess, we fill in with saddles which are smooth. On the other hand, there's a different kind of path integral that one can do, where one fixes the area of the HRT surface. So you fix the area as a boundary condition and also the asymptotic boundary conditions here. This, in general, would lead to some sort of conical deficit angle at the HRT surface, and this is allowed by the boundary condition. So we're just using a different boundary condition where we're fixing the area to a particular value. We're basically restricting fluctuations in the area. And what was proposed in these papers is that there's a nice connection between the random tensor networks and gravity path integral, where we restrict to such fixed area states. In fact, there are non-perturbative effects that are captured by the tensor network, which are exactly the same as what you would see in gravity. When you do this random average, you find something like a sum over permutation. So when you say compute the Renyi entropies, you take n copies. And in the tensor network, there's something analogous to gluing the copies together in some way. And this is exactly in one-to-one correspondence with a sum over topologies in the path integral. The picture looks something like this. The advantage of these fixed area states is once you have one copy of them, you can just use this to compute trace row cube, because you can just glue them together. And that's a solution which has the given area that you prescribed. You basically don't have to solve for the equations of motion again. This is the usual complication with Renyi entropies, but this makes it simple. And this is represented in one-to-one correspondence with a sort of cyclic gluing structure in the tensor network. There's an exact correspondence between these. So non-perturbative effects in the gravity path integral can be captured by this stupid model of the random tensor networks. And so we also went about doing the reflected entropy calculation in such a setting. And what you find is it's hard to do the resolvent trick. So you can't really clarify what happens at the phase transition, but there are still some interesting effects that you can see, which I think will morally show up in gravity. And the feature is the following. So when we try to compute the reflected entropy, there's a disconnected saddle, which was the same as what we saw before, and a connected saddle. But when we take the entropy to be some Renyi entropy with some finite n, what we find is there's a back reaction between the brane that corresponds to the index m, which prepares the state itself, and the Renyi index n. So there's some sort of back reaction that there's a competition between these two terms, which leads to some sort of squeezing of the cross section. So the cross section looks more like this, where it's a slightly smaller cross section. And what fills up the saddle is a replica symmetry breaking region in the middle between the entanglement wedge and the squeezed entanglement wedge. And I think, and as you take n goes to 1, the back reaction vanishes and you end up with the full cross section. So I think this is something that is a feature that we should be able to see in gravity, although I don't have a concrete model where I can see it yet. But it tells you a heuristic picture for the non-perturbative effects. And this can be checked with numerics as well. Okay, good. So now let me just briefly mention, having inspired you to think about tensor networks as useful toy models, there's a nice picture for the canonical purification, which might help answer what Sandeep was asking about earlier. So the model for, so we can think of the calculation in the West Coast model in a sort of different way, where we do something like ER equals EPR. So suppose we converted all the entanglement of the radiation into some sort of a wormhole. So we have this 3-boundary wormhole. We can think of A and B as R1 and R2 in the previous calculation, and C as the black hole. Then we have some sort of geometric connection. Now we've gotten rid of all the quantum effects, but we have these geometric connections. And this can be easily represented by a single tensor network. It captures all of the features where the horizon areas are just fixed by the bond dimensions in this tensor network. And the effective description that we saw was of these two super selection sectors, one of the pole and one of the mount. This is in fact exactly consistent with taking this 3-boundary wormhole and gluing it in 2 different ways. So first we consider taking these disconnected portions and gluing them onto their doubled copies. So we end up with these tubes, which are 2 separate 2-boundary wormholes. And here it's clear that there's no geometric connection between A star and B star. So the entropy is 0. So this corresponds to the pole. It's the disconnected answer. On the other hand, if we took this entire region and glued it on the entanglement wedge, then we end up...
Sorry, which entire region? Say again, I missed that.
Sorry, it was this entire region. So the connected entanglement wedge. If we take the connected entanglement wedge and glue it together, then we get some sort of 4-boundary wormhole, where now we can use RT. And what does RT tell us? Well, if you're computing the entropy of A star, then the 2 possibilities are this surface and this surface, or these 2 horizons, the horizons of B star or the horizons of A star. But we started with the fact that we were using ER equals EPR to convert the entropy of the radiation into an area. And so these areas are exactly analogous to what we were calling log K1 and log K2 earlier. And so this is sort of a geometric picture for what was happening in the previous calculation. And these 2 are again honest saddles because we're gluing across an extremal surface. So we have good initial data here. Okay. And this connection is in fact even richer, because you could consider situations where there is a non-trivial entanglement wedge cross section in the middle, which splits the region connecting A and B. And now this is not what happened in the West Coast model, but this is some sort of generalization of it, where now what you can possibly do is you have the usual saddles. You do have the saddles which were the connected and disconnected ones, but you can also take 2 copies of these 4-boundary wormholes and glue them together. When you glue them together, what you get in this following fashion. You get a genus 1 four-boundary wormhole. If you compute now the entropy of AA star, what do you get? Well, when you compute the entropy of AA star, the minimal cross-section is actually this green surface and this green surface. Since the original green surface itself was twice EW, you end up with an answer that's 4 times EW. And this sequence goes on in the genus expansion. You can keep gluing 4 boundary wormholes together to get higher and higher cross sections. So you expect a spectrum of the following form, where there's a pole, there's a mound corresponding to 2 EW, which is this geometry. There's a mound corresponding to 4 EW, which is this geometry, and so on. And there's a full genus expansion in this. Now, this is actually something we can find from numerics, and there's a nice description of this using what's called temporally Lieb algebras, and this is some work in progress, but we can see these features in the tensor network, and we expect this to be true of gravity as well. So these saddles, these higher genus saddles, actually play an important role near the phase transition and don't affect the answer anywhere away from the phase transition. So the holographic proposal is pretty much intact, but there are these interesting saddles that we find near the phase transition. And all of this comes from the tensor network description because it captures these non-perturbative effects. Okay, so with that, I'll finally like to summarize. So in this talk, I'd like you to remember that I showed that SR equals 2EW in these toy models, and in fact, more generally in these tensor networks. And in the particular toy model, we could resolve this phase transition to understand the page curve for reflected entropy. More generally, these random tensor networks are great toy models for the replica trick in fixed area states in ADS-CFT. And this should be exploited more. I think like we should really use these better to understand more entanglement measures and so on, to understand what non-perturbative effects play a role in gravity. And further, we also saw that there's this nice effective description where canonical purification leads to building up geometry. So we started with some 3 boundary wormhole, and then by canonical purification, we ended up with 4 boundary wormholes and higher genus 4 boundary wormholes. And I think this pattern will keep replicating, at least in the context of wormholes. So this is something where we can use entanglement. So it was some initial entanglement structure, which we can use to convert it into geometry, at least in this toy model where we have few observables. And it would be nice to basically push the limits on tensor networks to bring it as close to gravity as possible. There are some generalizations of this that I don't want to talk about. Basically, in the context of islands, there's some generalization to this formula, which is basically captured by the West Coast model. And we can also consider some sort of modular flowed version of this, but I won't give more details on this. But anyway, some future directions I'm interested in is, as I said, building better models of gravity using these tensor networks. There are a lot of issues with tensor networks, so we're trying to resolve those, like understanding time dependence, how the commutation relations of gravity can come out of tensor networks, and so on. There's a very important feature that I think led to a lot of confusion here as well, which was ensemble averaging. Ensemble averaging is very interesting because JT gravity has been shown to be this ensemble average, but also in the random tensor networks, there's some sort of ensemble average picture. So there's it seems to be this universal feature that ensemble averaging leads to nice geometric pictures, and I'd like to understand that better. And further, as I said, the reflected entropy was one particular multipartite entanglement measure, but we can consider many such and understand better the entanglement structure relevant for holographic states. With that, I'd finally like to thank you. So thank you so much for listening.
Okay, thank you so much, Pratik, for a wonderful talk and a very clear talk. Let's all applause.
Thanks.
Okay, and I'm also sorry for cutting some of the discussions short. So I think now is a good place, if Pratik is not too exhausted, to ask him some more questions.
I have to run, actually, but Pratik, let me just ask one question, and I apologize to everyone for going first. Please excuse me. Which is, if you had asked me how to measure the entropy in some subsystem consisting of 2 parts, R and R prime, A and B, whatever, I would have said, okay, compute the mutual information. That will tell you how different is the density matrix for AB compared to rho A tensor rho B. And my question to you was, why is this better?
Good.
Or you don't, I mean, that may be needlessly irritating a question, but if you just did something with mutual information, do you get similar pictures and connect and so on with it?
You don't. Okay, so good. So the mutual information will, I mean, since we're just computing some linear combination of entropies, it accesses exactly the information that the Ryu-Takayanagi surfaces had anyway. Yeah. And it doesn't have any nice picture of constructing surfaces deeper in the bulk. One reason why the reflected entropy is useful is because it has this nicer picture for other surfaces in gravity that we would care about. A second reason is, as Onkar will probably be able to say better, like there's a difference between reflected entropy and mutual information in holographic states, which actually is very important. And what we had showed in our paper, and it was further emphasized in Onkar's paper, is that tripartite entanglement in holography, you can measure that there has to be tripartite entanglement in holography because of this difference between reflected entropy and the mutual information. This was something that was actually in contention all the way until like a year back or 2 years back, where people proposed that gravity actually has a very simple entanglement structure. It's all bipartite. Like you just take any system and you can decompose it into bipartite connections. And we showed that this was not true and it was much richer. So this is one reason you could care about it.
Okay. Okay, great. Thank you for a great talk, and see you around, and hopefully in Mumbai. I'm going to run off. Thanks, everyone. Sorry for. Thank you. Thanks.
So, Pratik, sorry, a small question. Why is it called a reflected entropy?
Good. So it's just some random name they came up with. It's basically this canonical purification. It has some. So in algebraic QFT, you can make this rigorous and. Using like Tomita-Takesaki theory, and the reflection I think comes from the fact that the Tomita, like the operator that's doing this is like a generalization of the CPT operator. It's like this J operator in Tomita-Takesaki theory. So it plays a key role. So it's sort of like a reflection in that sense. I don't know if there's any other reason. I think it's just a term that Faulkner came up with. So I don't know.
Hi, Pratik. I wanted to get one or two things straight about the structure of the states, if you don't mind.
Yes.
So from Onkar's comments, I've taken away the following impression, and please tell me if this is right. First, there's a totally boundary description. The boundary description consists of this random matrix model coupled to radiation.
We don't need to bring in the radiation at this point. Like we can just describe a state of the brains and the black hole system. That already is a random matrix. Like that already is a matrix ensemble.
I understand, but I thought you were going to compute entanglement entropy of radiation states, so you needed radiation.
Yeah, but I thought your issue was even before that. But okay, yes.
I'm trying to understand your system. Yeah.
Yes. So
your system consists of a random matrix model and a radiation system. Is this right? Yeah. On the boundary?
Yes.
Okay. And the bulk dual description of it is JT gravity coupled to radiation. This is right? JT gravity and the brain coupled to radiation.
Entangled with radiation, yes. I mean, there's no explicit like interaction, so I won't say coupled.
Fine, yes. JT gravity and the brain and radiation, let's say.
Yes, agreed.
Okay, excellent. So now, Onkar's comment was that there were special kinds of states, not necessarily orthogonal, in the boundary description, in the matrix model part, that was shown to have a dual description in terms of boundary states on the brain. Sorry, bulk states on the boundary brain, on this end of the world brain. Is this right?
Yes.
This is accurate? There are special states that you can just write down in the matrix model, some coherent state kind of states, which
they're just
they're not coherent states. They're random superpositions of energy eigenstates.
Okay, random superpositions of energy eigenstates, which have dual descriptions as states on the end of the world brain.
Yes.
Is this completely accurate? Okay, excellent. Now, in these random superpositions of energy eigenstates have some labels. Presumably, Can you help me to understand what these labels are? I'm trying to understand what the IJ labels are, basically. I'm heading towards it.
Okay, so I feel like it'll be helpful. Okay, so if you don't mind, can I just share their original paper? Maybe that'll be useful.
Okay.
Okay, let me, well, just a second.
Presumably it's some UN kind of label, right? You're superposing.
Is precisely what we're talking about. So this is the definition. This is the definition of the states.
And can you tell me what is the CIA?
The CI are random coefficients, which are these complex Gaussian random variables. And so it's this is what Omkar was saying. It's a random superposition over energy eigenstates. So
but labeled by I. So where is the I labeling in the CIA? I'm sorry, we can do this offline actually. If this is going to be,
that's fine. Like I is just the label that we're thinking of as the brain label.
No, but in this just matrix model, it's somehow weighting some states over the others, right?
No, it's just completely random.
But then the left hand side doesn't depend on I.
Well, it does, because like for a single instance, it does. When you average.
So then CIA.
So can you not take it to be just coefficient of a particular radiation state?
Yeah.
Maybe I thought that's what defines what subscript I of psi is. I don't know. I mean, that's what I thought. But
a radiation state, like I think we should call it a brain state, because maybe that's the confusion. I would like to say it's the label of the end of the world brain.
Right, but at the moment we're on the boundary. There's only the matrix model. So the CIA somehow depends on I, right?
Yes. So the boundary system it's some Hamiltonian, which is the black hole system, and it contains degrees of freedom, which are these I. There are these I labels, and the I label here is
well, the boundary system. I thought its spectrum was given by EA.
Right.
Well,
so the EAs are the energy eigenstates of the boundary system, and let's define these states psi I also in the boundary system, which are these particular superpositions of energy eigenstates. And for the ith state, we will pick the coefficients of that superposition to be CIAs.
And these are picked independently. So one instance of random superposition and then another one.
Yes.
So the first choice is the I equals 1, second choice is I is equal to 2, and so on.
Yes.
Now I understand. Thank you. And okay, and then you say that okay, if I take I is equal to 1 to 100 and I is equal to 101 to 200, these are your IJ.
Yes. For example, yeah.
And because there are so many states, the chance that they overlap is sort of small.
Exactly.
I see. And is the idea that that this is a good model for early and late radiation, for instance? So I thought what we really wanted to do was to model the entanglement between some part of the radiation and another part of the radiation.
We want to model the entanglement between the exterior and the interior radiation, and this psi I is like the interior state, and we're explicitly entangling it with this exterior radiation, which was my R1, R2 system.
Well, sorry, I thought that the radiation was entangled, that there were two parts of the radiation, I part and J part. Early and late radiation.
Sorry. So the radiation, the exterior radiation was artificially split into the I part and the J part, which was like my R1 and R2.
Yes. So that's what I'm talking.
And those are entangled with the brain. So we don't need to talk about I and J for this purpose. Even if we use a single index, the radiation, which was the exterior system, like the R1, R2 system, was just entangled with the states of the brain, which are defined by these psi I of betas. So we had something like sum over I on the radiation, psi I of beta on the black hole.
Right. But then you used some properties of this state, like the summing over I and J separately in your calculation. I'm trying to see that that is reasonable for the states that come out of actually producing radiation. So if I understood right, the early radiation is entangled with some matrix model state. The late radiation is entangled with some other matrix model state. And you say that both of these are essentially arbitrary, that it's a good model to take them to be arbitrary, independent, random superpositions of eigenstates. And because they're arbitrary and independent, their overlap is very small unless the Hilbert spaces become very large or something.
Yes, yes.
And just the last question about this, sorry, is that a reasonable, I have no intuition, is that a reasonable picture for what the actual radiation state will be entangled with?
It seems like, I mean, all of these calculations seem to suggest that that's what's happening, because like you could face the same issue with other more nuanced models. Well, maybe I should say this, like,
why not? You say why not?
I don't know an independent way to say that this is a good model. Sorry. I think it's just we're believing that this is a good model.
Okay, thank you very much. Now I understand the setup well now. Thank you, and thank you, Onkar, for helping.
Oh, no, of course. But just to address your second question, or the last question, Pratik, is it possible to try and repeat these calculations in, say, the East Coast model? I realize that may be very hard to do, but just
I think in principle you could. I think the problem is that you don't have good control over like possible like loop corrections and so on. Like the advantage of JT gravity was that it was one loop exact and we could do all of this non-perturbative sum and so on. So there are like basically two camps. One would say like JT gravity is the way to go. Like there's ensemble averages, it's clear from that. But then you could say that, oh, there are loop corrections which will totally change the answer. So you don't need the ensemble average. So it's almost like a matter of belief at this point. Like we need some other way to really calculate this.
Right. Yeah, and the other question I had was about these higher genus solutions that you found in your random matrix description. I was just trying to like understand why only one of them, in particular the P1 guy or the 2 times EW guy, that somehow dominates at some point, but the other ones don't.
Good. So the real calculation we do is look at something like trace of. So we look at, say, something like rho AB to the m over 2, some operator insertion, rho AB to the m over 2, right? We'd like to compute this using the path integral and see what the geometry is. So a simple representation for this is like just in terms of the tensor network, it's just we have copies 1, 2, 3 up till m over 2 and then m over 2 plus 1 and so on up till m. So basically you're computing something like trace rho AB to the m o, something like that. And there are different gluings that you can do. So let's take any possible m. Then so you can have gluings like this, something like this, and so on. You can have all possible permutations. And this index is basically just the number of lines cutting the middle line. I mean, this eventually, when you do the calculation, the interpretation of this genus is how many indices cross the middle line. So what you can do is use the path integral, compute what these weights are explicitly. So you can compute P0, P1, P2, and so on. It just so happens that P0 and P1 are the only things that dominate on either side. It's I think in principle reason why this couldn't dominate. So but it calls into question things. I mean, so the starting that of this was like we use this intuition that you can just take 2 copies and glue them together and get this thing. But it seems like that isn't sufficient somehow. Like there's some corrections we need to be careful about and stuff.
I see. Okay, thank you.
Thank you for that.
Sorry, Pratik, one question. The fact that this phase transition occurs at the page time, I don't know whether, I think this is, so is that something that one should have a priori expected just from, so that's one question.
The reflected entropy, you mean?
Yeah.
No, I mean, the only arguments for the reflected entropy previously were the saddle point approximation from the path integral, which only held far from phase transitions. So we didn't really know what the answer should be. However, in this model, at least we've motivated that there's this simple ansatz where you get this nice answer, where it's a sum over selection sectors of these different geometries. There's no way to guarantee that this will always be the case, but I'd like to understand better how much we can push this model, like this effect.
And also, you as you mentioned, in the early time, you expect the two radiation Hilbert spaces R1 and R2 to be individually entangled with the black hole. That's why the reflected term should be kind of zero. But later on, it's also entangled with each other along with the black hole, right? So, and you're saying somehow you had this picture of cutting, so that when this P1 term is non-zero, it must be equal to log minimum log K1, log K2, something like that you had. But why can't it be that it is little bit entangled with R2? That R1 is a little bit entangled with R2 and a little bit entangled with black hole, giving you this particular measure to be somewhere in between. Not necessarily log of.
Oh, good. So a simple picture to understand that is this one. So when we say that, so in the connected phase, it's not that A and B are just entangled with each other, because the black hole has to be entangled with something. So C is really entangled with the combination of AB, and that's visible from this picture. So when we consider the connected cross section, then there is, so really here I'm using some sort of ER equals here. The geometric connection between these two is representative of some sort of entanglement, but because of the connection between C and A as well, and C and B as well, there's also entanglement too. So the reflected entropy, being the entanglement wedge connection, already takes that into account.
I see. Yes. Okay.
And one more
but in what case would it not just be log of K1 then?
So that's a very good question. Like, I mean, it seems like at least far from phase transitions, it's always going to be log K1, log K2. Okay. What I was describing here were these two models. So in this first model was, we considered the entanglement wedge cross section only to be these horizon areas, and that gave us this effective description. The second model was a little bit more nuanced because there was a non-trivial entanglement wedge cross section which split them. So it's sort of, there was this geometric connection and it was split by the green surface. And in that case, at least there was a more refined construction, but still the answer was twice of that green surface. So at least in the saddle point approximation, where far from phase transitions, I don't think there's any situation where you wouldn't get twice entanglement wedge. But I mean, as we were just discussing, like, it's possible that in other models you can make maybe some of the other saddles to dominate or something like that, where you get a different. I don't know.
Thanks.
And Pratik, in your JT gravity calculation, presumably you can also compute the reflected entropy between, say, the black hole system and one of the radiation systems.
That's an excellent question. We haven't managed to do that yet. It is a little more technically complicated, but yes, that's what I'm working on right now. Like,
okay. I was just wondering whether that would somehow give you a geometric contribution to the entanglement wedge cross section.
So there was an interesting feature in that model which simplified it, and that simplification was this form of the state. Let me go back to. It was this state. So in this state, the density matrices of R1 and R2, I mean, we just picked sort of a flat spectrum for them. And we chose to compute the reflected entropy on those systems. The non-trivial part of considering B is that it has this non-flat spectrum. So there are like these energy fluctuations there.
Yeah.
And I expect that it'll be a much more complicated situation. Like even in this calculation, at least in this calculation, what happens when you include corrections from the canonical ensemble, it's just that it changes. I mean, the form of the spectrum stays the same, but it just changes the spread of the weights and so on. But I imagine that it'll be much more complicated once you actually consider one of the systems themselves to be having a non-flat spectrum.
I see. But just do you expect to find a geometric term in the reflected entropy in that case?
I would expect so. I would expect that the answer would be min of the black hole entropy and log K1.
Yeah, that's what. Yeah, that's what I would have thought. Yeah.
But I think it's interesting to look at what happens there.
Okay. Thank you so much.
Yeah, are there more questions? I guess not. Thanks a lot, Pratik, again for a very nice talk and answering all our questions so very patiently.
Oh yeah, thank you so much. It was really fun.
Thanks for the patience, Pratik.
Oh, it was great. I really hadn't expected so many questions. It was a very fruitful discussion. Thank you so much for that.
Yeah. Thank you so much again, Pratik. Great talk. Thank you.
Thank you very much. Bye-bye.